Hello, and welcome. I'm so glad you're here with me tonight, settling into this quiet moment at the end of your day. Perhaps you've been carrying the weight of tasks and thoughts, the endless motion of the waking world, and now you're ready to let all of that drift away for a while. You don't need to do anything right now except breathe, rest, and allow yourself to sink a little deeper into comfort. Tonight, we're going to explore something truly gentle, something that exists all around you and within you, something so fundamental and so quietly beautiful that it deserves to be told as a bedtime story. We're going to talk about molecular bonds and stability, about the invisible threads that hold the universe together in the most peaceful, predictable ways. You might think that chemistry is all about reactions and explosions, about bubbling beakers and dramatic transformations. But at its heart, chemistry is about connection, about the way tiny particles find each other in the vastness of space and decide, in their own wordless way, to stay together. It's about balance and harmony, about forces that seek the lowest energy, the calmest state, the most restful configuration. And there's something deeply soothing in that. If you'd like to join me on more journeys like this one, you're welcome to follow along, but there's no pressure at all. Right now, all that matters is that you're comfortable, that your breathing is easy, and that you're ready to let these ideas wash over you like a warm, gentle tide. Let us begin by thinking about atoms themselves, those impossibly small building blocks of everything you see and touch. An atom is mostly empty space, a fact that might sound strange, but is actually quite calming when you consider it. At the center sits a nucleus, dense and stable, made of protons and neutrons huddled together. And far, far away in atomic terms, like stars orbiting a distant sun, electrons trace their paths in clouds of probability. These electrons don't move in neat circles the way old diagrams might suggest. Instead, they exist in regions of space where they're most likely to be found, soft blurs of possibility rather than fixed points. And it's these electrons, these wandering clouds of negative charge, that make all bonding possible. When two atoms come close to each other, their electron clouds begin to interact. It's not a violent meeting, not a collision, but rather a kind of conversation carried out in the language of electromagnetic force. Electrons repel each other because they share the same negative charge, and yet they're also drawn toward the positive nuclei of nearby atoms. It's a delicate balance, a push and pull that settles into something stable when the conditions are just right. And when that balance is found, when the forces align in a way that lowers the overall energy of the system, a bond forms. The atoms, once separate, become partners in a molecular dance that can last for fractions of a second or for billions of years. There is something profoundly restful about the idea that atoms seek stability. They don't struggle or strain toward chaos. Instead, they naturally drift toward arrangements that require the least energy, that feel, in a sense, the most comfortable. This is a fundamental principle of nature. Systems tend toward their lowest energy state. It's why water flows downhill, why heat spreads from warm to cool, and why atoms bond in the particular ways they do. When you think about it, the entire universe is constantly settling, relaxing, finding its most peaceful configuration. And you, lying here tonight, are part of that same gentle tendency. The simplest bond, the one we might think of as the most straightforward, is the covalent bond. In a covalent bond, two atoms share electrons. Imagine two atoms approaching each other, their electron clouds beginning to overlap. In that overlap, in that shared space, electrons can belong to both atoms at once. It's a kind of partnership, a mutual agreement that benefits both parties. The shared electrons spend time near both nuclei, and this arrangement holds the atoms together with a quiet, steady force. Hydrogen molecules are a beautiful example of this. Two hydrogen atoms, each with a single electron, come together and share those electrons. The result is a stable molecule, H2, floating peacefully through space or drifting in the air you breathe. What's remarkable is how strong these shared electron bonds can be, and yet how they form without any conscious intent, without any effort. It's purely a matter of physics, of charges and distances and quantum mechanics. But the result feels almost intentional. The atoms find each other, share what they have, and become more stable together than they ever were apart. There's a kind of quiet poetry in that, a reminder that connection and stability often go hand in hand. Not all bonds involve sharing, though. Some bonds form through a different kind of partnership, one based on giving and taking. These are called ionic bonds, and they emerge when one atom has a strong tendency to lose an electron while another has an equally strong tendency to gain one. Imagine a sodium atom with a single electron in its outermost shell, loosely held and easy to release. Nearby is a chlorine atom with 7 electrons in its outer shell, just one short of a complete, stable set of 8. The sodium atom releases its electron, becoming a positively charged ion, and the chlorine atom accepts it, becoming negatively charged. Now, opposite charges attract, and the two ions are drawn together, held by the simple, powerful force of electrostatic attraction. The resulting compound, sodium chloride, is table salt, one of the most stable and familiar substances on Earth. It forms crystals that can last for geological ages, structures so regular and repeating that they seem almost architectural. And yet, they form naturally, spontaneously, whenever sodium and chlorine meet under the right conditions. There's no blueprint, no plan, just the quiet logic of charge and stability guiding the process. Ionic bonds tend to be quite strong because the attraction between opposite charges is straightforward and unambiguous. But they're also somewhat rigid. The ions lock into place in their crystal lattices, each surrounded by partners of the opposite charge, and they stay that way until something disrupts the structure. Dissolve salt in water, though, and the ions drift apart, free to move independently, yet still stable in their charged states. It's a different kind of stability, more fluid, but no less real. Then there are bonds that are weaker, gentler, more temporary, but no less important for the roles they play. These are the hydrogen bonds, and they are among the most soothing bonds to contemplate because they are so subtle, so easily formed and broken, and yet they shape so much of the world. A hydrogen bond forms when a hydrogen atom, already covalently bonded to an electronegative atom like oxygen or nitrogen, finds itself attracted to another electronegative atom nearby. It's not a full bond, not a sharing or a transfer, but rather a kind of magnetic pull, a whisper of attraction. Water is held together by hydrogen bonds. Each water molecule, with its bent shape and its polar character, can form hydrogen bonds with up to 4 neighbors. These bonds are constantly forming and breaking, a dynamic dance that happens trillions of times per second in every drop of water. And yet, despite their weakness compared to covalent or ionic bonds, hydrogen bonds give water its unique properties, its high boiling point, its ability to dissolve so many substances, its tendency to form that delicate lattice structure we call ice. In ice, the hydrogen bonds lock the water molecules into a spacious, open framework, which is why ice floats. It's lighter than liquid water, a rare and fortunate quirk of chemistry that keeps lakes from freezing solid and allows life to persist beneath the ice. Hydrogen bonds are also the reason DNA holds its double helix shape. The 2 strands of the helix are connected by hydrogen bonds between complementary base pairs, adenine with thymine, guanine with cytosine. These bonds are strong enough to keep the strands together, but weak enough that they can be pulled apart when a cell needs to read or copy the genetic information. It's a perfect balance, a molecular design that allows for both stability and flexibility, for permanence and change. As you lie here, your body is full of hydrogen bonds. They're holding proteins in their folded shapes, allowing enzymes to recognize their targets, keeping the membranes of your cells intact. Every breath you take, every thought you think, depends on the quiet work of these gentle bonds. And they ask nothing of you. They simply exist, doing their work in the background, part of the seamless, unconscious harmony of your biology. Let's drift now to the idea of bond energy, the amount of energy required to break a bond. This is a measure of stability, a way of quantifying how much two atoms want to stay together. A high bond energy means a strong bond, one that takes a lot of energy to break. A low bond energy means a weaker bond, more easily disrupted. But even weak bonds have their place and purpose. The universe doesn't favor only the strong. It also relies on the flexible, the temporary, the bonds that can form and dissolve as needed. When a bond forms, energy is released. This might seem counterintuitive at first, but it makes sense when you remember that bonding lowers the energy of the system. The atoms are more stable together, so they settle into a lower energy state, and the excess energy radiates away, often as heat. When a bond breaks, that energy must be supplied from somewhere else. It's an investment, a cost paid to separate what was joined. And this balance, this constant exchange of energy as bonds form and break, is part of the rhythm of chemistry, the heartbeat of molecular change. In your body, enzymes are constantly making and breaking bonds, building up complex molecules and tearing down others. But they do it gently, efficiently, using the energy from one reaction to power another. It's a web of interconnected processes, all humming along at body temperature, all perfectly balanced. There's no waste, no chaos, just the smooth operation of biochemical machinery that has been refined over billions of years. Now let's think about molecular geometry, the shapes that molecules take when atoms bond together. These shapes are not arbitrary. They emerge from the simple principle that electron pairs, whether bonded or unbonded, repel each other and try to get as far apart as possible. This is called VSEPR theory, which stands for valence shell electron pair repulsion, but you don't need to remember that name. What matters is the idea. Electrons push away from each other, and the shape of the molecule is the result of that pushing. A molecule of methane, for example, has a carbon atom at the center bonded to 4 hydrogen atoms. The 4 bonding pairs of electrons arrange themselves as far apart as possible in 3-dimensional space, which creates a shape called a tetrahedron. If you could see it, it would look like a pyramid with a triangular base, perfectly symmetrical, perfectly balanced. This shape is not imposed from outside. It simply emerges from the repulsion of electrons, from the atoms finding their most comfortable arrangement. Water, as we mentioned before, is bent rather than linear. The oxygen atom has 2 bonding pairs connected to hydrogen atoms, and 2 lone pairs of electrons that aren't involved in bonding. Those lone pairs take up space and push the bonding pairs closer together, creating a bent shape with an angle of about 104.5 degrees. This shape is crucial. It makes water a polar molecule, with a slight positive charge on one side and a slight negative charge on the other. And that polarity is what allows water to dissolve salts, to form hydrogen bonds, to be the universal solvent that makes life possible. Every molecule has its own shape, determined by the number and arrangement of its bonds and lone pairs. Some are linear, some are trigonal, some are octahedral, and each shape influences the molecule's properties, its reactivity, its interactions with other molecules. Shape and stability are intimately connected. A molecule that can adopt a low-energy shape is more stable, more likely to persist, more content in its existence. Let's consider now the idea of resonance, a concept that might sound complex, but is actually quite calming when you understand it. Some molecules can't be accurately represented by a single structure. The electrons are spread out, delocalized, shared across multiple atoms in a way that doesn't fit neatly into our simple pictures of bonds. Benzene is the classic example. It's a ring of 6 carbon atoms, and you might imagine alternating single and double bonds around the ring. But in reality, the electrons in those bonds are smeared out evenly across all 6 carbons. The molecule doesn't flicker between two structures. It exists as a stable hybrid, a blend of possibilities. This delocalization makes benzene more stable than you'd expect. The electrons have more room to spread out, more space to occupy, and that lowers the energy of the system. It's called resonance stabilization, and it's a common feature in many organic molecules. The electrons aren't confined to a single bond. They're free to roam across a larger region, and that freedom brings stability. It's a beautiful paradox. By being less fixed, less rigid, the molecule becomes more stable, more at ease. Aromatic compounds, which include benzene and many related molecules, are everywhere in nature. They're in the fragrance of flowers, in the structure of DNA bases, in many of the molecules that give foods their flavors. And they're all stabilized by this gentle spreading out of electrons, this refusal to be pinned down to a single configuration. Let's turn our attention now to the concept of electronegativity, a property of atoms that describes how strongly they attract electrons in a bond. Some atoms, like fluorine and oxygen, are highly electronegative. They pull electrons toward themselves with great force. Others, like sodium and potassium, are much less electronegative. They hold their electrons loosely, willing to let them go. When two atoms with different electronegativities form a bond, the electrons aren't shared equally. They spend more time near the more electronegative atom, creating a polar bond, a bond with a slight charge imbalance. This polarity is subtle, but it has profound effects. It's why water is polar, why some molecules dissolve in water and others don't, why certain reactions happen and others don't. The distribution of charge in a molecule determines how it interacts with the world, and that distribution is shaped by the electronegativities of its atoms. It's a quiet property, not something you can see or touch directly, but it influences everything. In a perfectly nonpolar bond, like the bond between two identical atoms, the electrons are shared exactly equally. There's no tug of war, no imbalance, just a serene symmetry. In a highly polar bond, the electrons are pulled strongly toward one side, creating a significant charge separation. And in an ionic bond, the pull is so strong that the electron is transferred entirely from one atom to the other. These are not distinct categories, but points on a spectrum, a gradual shift from sharing to taking, from balance to imbalance. Let's think now about the energy landscape of a bond. Imagine a graph where the horizontal axis represents the distance between two atoms and the vertical axis represents the potential energy of the system. When the atoms are far apart, the energy is high because there's no interaction, no bond. As they come closer, the energy drops. The attraction between the nucleus of one atom and the electrons of the other pulls them together, and the system becomes more stable. But if they get too close, the energy shoots up again because the positively charged nuclei repel each other, and the electron clouds are forced into the same space. There's a sweet spot, a distance where the energy is at its minimum, and that's the bond length. It's the distance at which the atoms naturally rest, held in balance by the competing forces of attraction and repulsion. This energy well is a comforting image. The atoms settle into it like a ball rolling to the bottom of a bowl. They don't need to be pushed or guided. They find their way naturally, drawn by the simple logic of physics. And once they're there, they stay, vibrating gently around that equilibrium position, content in their stability. Of course, bonds can be stretched or compressed a little bit. If you pull the atoms apart, the energy goes up and the bond resists, pulling them back together. If you push them closer, the energy also goes up and the bond pushes back. It's like a spring, flexible, but with a preferred length. This is why molecules vibrate. The atoms are constantly moving, oscillating around their equilibrium positions, absorbing and releasing tiny amounts of energy in the form of heat. At room temperature, this vibration is gentle and continuous, a molecular hum that never stops. Let's consider the idea of bond order, which is simply the number of shared electron pairs between two atoms. A single bond has a bond order of 1, a double bond has a bond order of 2, and a triple bond has a bond order of 3. Higher bond order generally means a stronger, shorter bond. A triple bond, like the one in nitrogen gas, is very strong and very short. The two nitrogen atoms are held together so tightly that nitrogen gas is remarkably stable and unreactive. It makes up about 78% of the air you breathe, and it just sits there inert and calm, not bothering with much chemistry at all. Double bonds are also strong, but they have a different character. They're shorter and stiffer than single bonds, and they restrict rotation. In a single bond, the atoms can spin freely relative to each other, but in a double bond, they're locked in place. This has important consequences for the shapes and properties of molecules. It's why certain molecules have cis and trans isomers, different arrangements that can interconvert without breaking the bond. And it's another example of how the details of bonding shape the macroscopic world. Let's drift now into the realm of metallic bonding, a type of bonding that's quite different from what we've discussed so far. In a metal, the atoms are packed closely together, and their outermost electrons are not bound to any particular atom. Instead, they form a sea of electrons that flows freely through the entire structure. The metal atoms, now positively charged ions, sit in this sea, held in place by the attraction to the surrounding electrons. It's a communal arrangement, a sharing that extends across millions and billions of atoms. This electron sea gives metals their characteristic properties. It's why metals conduct electricity. The electrons are free to move, carrying charge from one place to another. It's why metals are shiny. The electrons can absorb and re-emit light of all frequencies, creating that lustrous gleam. And it's why metals are malleable and ductile. The atoms can slide past each other without breaking bonds, because the bonding isn't localized between specific pairs of atoms. It's a fluid, flexible kind of stability, very different from the rigid lattices of ionic compounds or the discrete molecules of covalent substances. When you hold a piece of metal in your hand, you're feeling the result of this electron sea. The coolness of a metal is due to its high thermal conductivity, another consequence of those mobile electrons. Heat energy is quickly carried away from your skin, making the metal feel cold even when it's at room temperature. It's a small, tangible reminder of the invisible bonding that holds the material together. Let's think about stability in a broader sense now. A stable molecule is one that doesn't spontaneously fall apart or react violently with its surroundings. It's content to exist, to persist over time. But stability is always relative. Some molecules are stable under one set of conditions, but not another. Water is stable at room temperature, but heated enough and it turns to steam, the molecules flying apart. Cool it enough and it becomes ice, the molecules locked into a solid lattice. The molecules themselves don't change. It's their arrangement and their energy that shifts. Chemical stability also depends on the environment. Oxygen gas is stable in the air, but in the presence of a spark and some fuel, it can participate in combustion, releasing energy as bonds break and new bonds form. The oxygen molecules aren't inherently unstable. They're just waiting for the right conditions, the right activation energy to react. And that's true of many molecules. They exist in a kind of potential state, stable for now, but capable of change if the circumstances shift. There's a concept in chemistry called kinetic stability versus thermodynamic stability. Thermodynamic stability refers to the energy of a system. A thermodynamically stable molecule is one that's at a low energy state, unlikely to change because there's no lower energy state to move to. Kinetic stability, on the other hand, refers to the rate of change. A kinetically stable molecule might not be at the lowest possible energy, but it's protected by a high activation energy barrier. It would take a lot of energy to get the reaction started. So even though the molecule could theoretically transform into something more stable, it doesn't because the barrier is too high. Diamond is a wonderful example of kinetic stability. Diamond is made of carbon, just like graphite, but in diamond the carbon atoms are arranged in a rigid, three-dimensional network, each bonded to four neighbors in a tetrahedral geometry. This structure is incredibly strong, which is why diamond is the hardest natural material. But thermodynamically, diamond is not the most stable form of carbon at normal temperatures and pressures. Graphite is. In graphite, the carbon atoms are arranged in flat sheets that can slide over each other, a much lower energy configuration. So technically, diamond should slowly transform into graphite, but it doesn't, at least not on any human timescale, because the activation energy for that transformation is enormous. The bonds in diamond are so strong and so locked in place that the atoms can't rearrange. Diamond is kinetically stable, trapped in a high-energy state by the very strength of its bonds. This is a comforting thought, in a way. Even when a system could theoretically change, it often doesn't, because change requires overcoming barriers. Stability isn't just about being in the lowest energy state. It's also about being protected from change by the structure and strength of bonds. You, too, are kinetically stable in many ways. Your body is constantly undergoing chemical reactions, but they're controlled, regulated, kept within safe boundaries by enzymes and membranes and all the machinery of life. You're not at thermodynamic equilibrium, which would be a state of no change, no life, but you're stable enough, protected enough to persist and thrive. Let's consider now the role of entropy in stability. Entropy is a measure of disorder, of the number of ways a system can be arranged. The second law of thermodynamics tells us that in an isolated system, entropy tends to increase over time. Things tend to spread out, to become more disordered, more random. But this doesn't mean that order and structure can't exist. It just means that when they do, they must be balanced by an increase in entropy somewhere else. When molecules bond, they often create order. The atoms are no longer free to wander. They're locked into specific positions relative to each other. This decreases entropy. But the energy released when the bond forms can increase the entropy of the surroundings, often by heating them up, spreading energy more widely. The overall entropy of the universe increases, even as local pockets of order form. So bonding is consistent with the second law. It's not a fight against entropy, but a dance with it, a way of creating structure while still allowing the universe as a whole to drift toward greater disorder. In living systems, this balance is even more striking. Life is highly ordered, highly structured, and yet it doesn't violate the second law because living organisms constantly take in energy, usually from sunlight or food, and release waste heat and entropy into their surroundings. We are islands of order in a sea of increasing entropy, maintained by the flow of energy through us. And at the molecular level, this means forming and breaking bonds, building up complex structures and tearing down others, all in a carefully regulated way that keeps us stable, keeps us alive. Let's think about the concept of hybridization, a way of describing how atomic orbitals mix to form new orbitals that are better suited for bonding. In an isolated carbon atom, the electrons occupy different types of orbitals: s orbitals, which are spherical, and p orbitals, which are dumbbell-shaped. But when carbon forms bonds, these orbitals blend together, hybridize, to create new orbitals that point in specific directions. In methane, carbon uses sp superscript 3 hybrid orbitals for equivalent orbitals pointing toward the corners of a tetrahedron. In ethylene, carbon uses sp superscript 2 hybrid orbitals, 3 orbitals in a plane, with one unhybridized p orbital left over to form a double bond. In acetylene, carbon uses sp hybrid orbitals, 2 orbitals pointing in opposite directions, with 2 unhybridized p orbitals forming a triple bond. This might sound technical, but the underlying idea is simple. Atoms rearrange their electron clouds to make the best possible bonds, to achieve the lowest energy and the greatest stability. Hybridization is just a mathematical description of that rearrangement. The atoms don't know they're hybridizing. They're just responding to the electromagnetic forces around them, finding the configuration that feels most comfortable. And the result is a rich diversity of molecular shapes and properties. The same element, carbon, can form single, double, or triple bonds, can create chains, rings, sheets, and three-dimensional networks, all because of the flexibility of its bonding. This is why carbon is the basis of organic chemistry, the chemistry of life. It's not that carbon is special in some mystical way. It's just that its electronic structure allows for such a wide range of stable bonding arrangements. Let's drift now to the idea of bond polarity and molecular polarity. We've talked about how individual bonds can be polar if the atoms have different electronegativities, but whether a molecule as a whole is polar depends on its shape. If a molecule is symmetrical, the individual bond polarities can cancel out, leaving the molecule nonpolar overall. Carbon dioxide is a good example. It has 2 polar C=O bonds, but they point in opposite directions, so the polarities cancel and the molecule is nonpolar. Water, on the other hand, is bent, so the 2 polar OH bonds don't cancel. The molecule has a net dipole, a separation of charge, making it polar. Molecular polarity affects how molecules interact with each other. Polar molecules are attracted to other polar molecules. Nonpolar molecules prefer other nonpolar molecules. This is the basis of the old saying, like dissolves like. Polar solvents like water dissolve polar or ionic substances. Nonpolar solvents like hexane dissolve nonpolar substances like oils and fats. It's a matter of compatibility, of matching the interactions between molecules. In your body, this principle is at work everywhere. Cell membranes are made of lipid molecules with nonpolar tails and polar heads. The nonpolar tails cluster together, away from the watery environment inside and outside the cell, forming a barrier. The polar heads face the water, interacting comfortably with it. This creates a stable, flexible boundary that keeps the cell's contents in and unwanted substances out. It's a structure built entirely on the principles of bonding and polarity, a molecular architecture that has been refined over billions of years. Let's consider now the concept of lattice energy, which is the energy required to completely separate the ions in an ionic solid. It's a measure of how strongly the ions are held together in the crystal lattice. High lattice energy means a very stable solid, one that's hard to melt or dissolve. Sodium chloride has a fairly high lattice energy, which is why it forms such stable crystals and why it has a high melting point. Magnesium oxide has an even higher lattice energy because the ions have higher charges, +2 and -2, instead of +1 and -1. The stronger charges mean stronger attraction, tighter binding, greater stability. Lattice energy is influenced by 2 main factors: the charge on the ions and the size of the ions. Higher charges increase lattice energy because the electrostatic attraction is stronger. Smaller ions also increase lattice energy because they can get closer together, and the force of attraction increases with decreasing distance. It's a simple relationship, but it explains why different ionic compounds have such different properties. Some dissolve easily in water, their lattice energy low enough that the interactions with water molecules can overcome it. Others are nearly insoluble, their lattice energy so high that the solid remains intact even in the presence of a good solvent. Let's think about coordination compounds. Molecules where a central metal ion is surrounded by other molecules, or ions, called ligands, that donate pairs of electrons to the metal. These are sometimes called complex ions, and they're incredibly common, especially in biological systems. Hemoglobin, the molecule in your blood that carries oxygen, is a coordination compound. At its center is an iron ion, surrounded by a ring-shaped ligand called a porphyrin, and it's this iron that binds to oxygen molecules, holding them gently until they're needed in your tissues. The bonding in coordination compounds is a kind of sharing, similar to covalent bonding, but with a twist. The ligands have lone pairs of electrons that they donate to the metal, forming coordinate covalent bonds. The metal accepts these electrons, filling its empty orbitals, and the result is a stable, often colorful complex. The colors of many gemstones, the blues and greens and reds, come from the way light interacts with the electrons in coordination compounds. The metal ions absorb certain wavelengths of light, promoting electrons to higher energy levels, and the wavelengths that aren't absorbed are reflected back to your eyes. These complexes are also remarkably stable. The metal and its ligands form a tightly bound unit that can persist in solution, in crystals, even in the harsh environment of a living cell. The stability comes from the multiple bonds between the metal and the ligands, each one contributing to the overall strength of the complex. It's a kind of molecular teamwork, where the whole is greater than the sum of its parts. Let's drift now to the idea of van der Waals forces, a catch-all term for several types of weak intermolecular forces. These include dipole-dipole interactions, where polar molecules attract each other, dipole-induced dipole interactions, where a polar molecule induces a temporary dipole in a nonpolar molecule, and London dispersion forces, which exist between all molecules, even nonpolar ones. London dispersion forces arise from temporary fluctuations in electron density. At any given moment, the electrons in a molecule might be slightly more concentrated on one side than the other, creating a temporary dipole. This temporary dipole can induce a dipole in a neighboring molecule, and the two molecules attract each other, just for an instant. But there are so many molecules, and so many of these fleeting interactions, that they add up to a measurable force. These forces are weak, much weaker than covalent or ionic bonds, but they're not negligible. They're the reason that nonpolar substances like oils and waxes can exist as liquids or solids at room temperature. They're the reason geckos can climb walls. The millions of tiny hairs on their feet create enough van der Waals interactions with the surface to support their weight. And they're part of the reason proteins fold into their specific shapes. The weak interactions between different parts of the protein chain guide it into a configuration that's stable, functional, and uniquely suited to its role. In a sense, van der Waals forces are the quiet background hum of molecular interactions. They're always there, always acting, even when stronger forces dominate. And they remind us that stability doesn't always require strong bonds. Sometimes, a multitude of weak interactions is enough. Let's think now about the concept of resonance energy, the extra stability that comes from delocalization of electrons. We mentioned benzene earlier, how its electrons are spread evenly around the ring rather than confined to specific bonds. This delocalization lowers the energy of the molecule, making it more stable than it would be if the electrons were localized. The difference in energy between the actual molecule and the hypothetical localized structure is the resonance energy. It's a measure of how much extra stability the molecule gains from resonance. Resonance energy is a gift from quantum mechanics. Electrons are not particles moving in fixed paths. They're waves of probability, and waves can spread out, overlap, interfere. When electrons delocalize, they occupy a larger region of space, and this spreading out lowers their kinetic energy. It's a bit like how a wave on a string has lower energy when the string is longer. The electrons settle into a more comfortable, lower energy state, and the molecule benefits from that. Many biologically important molecules have significant resonance stabilization. The bases in DNA, the amino acids that make up proteins, the pigments that capture light in photosynthesis, all of these have delocalized electrons that contribute to their stability. It's part of why these molecules can exist and function in the complex, dynamic environment of a living cell. Let's consider the idea of bond length and bond strength. Generally, shorter bonds are stronger bonds. This makes intuitive sense. If the atoms are closer together, the attractive forces between them are stronger. Triple bonds are shorter and stronger than double bonds, which are shorter and stronger than single bonds. But bond length also depends on the size of the atoms involved. A carbon-carbon single bond is shorter than a silicon-silicon single bond because carbon atoms are smaller than silicon atoms. And a bond between a small atom and a large atom will have a length somewhere in between. Bond length is a measurable quantity. Scientists can use techniques like X-ray crystallography to determine the precise positions of atoms in a molecule. And from that, they can calculate bond lengths to within a fraction of an angstrom, a unit so small that 10 billion angstroms fit into a single meter. These measurements reveal the hidden architecture of molecules, the exact distances and angles that define their shapes. And they confirm what theory predicts, that bond length and bond strength are intimately connected, two sides of the same coin. Let's think about the role of temperature in bonding and stability. At absolute zero, the coldest possible temperature, atoms would be perfectly still. There would be no vibration, no motion, just the static arrangement of nuclei and electrons. But absolute zero is impossible to reach, and even at very low temperatures, atoms vibrate. As temperature increases, the vibrations become more energetic. The atoms oscillate more widely around their equilibrium positions, and the molecule as a whole moves and tumbles through space. At high enough temperatures, the vibrational energy can become so great that bonds begin to break. The atoms pull apart, and the molecule dissociates. This is why most substances melt or boil when heated. The thermal energy overcomes the forces holding the atoms or molecules together, and the orderly solid or liquid becomes a disordered gas. But even below the melting point, temperature affects stability. A molecule at high temperature is more reactive, more likely to undergo chemical change, because it has more energy to overcome activation barriers. In your body, temperature is carefully regulated. You maintain a nearly constant internal temperature, around 37 degrees Celsius, because the enzymes and other proteins that run your biochemistry are optimized for that temperature. Too cold, and the reactions slow down. Too hot, and the proteins begin to denature, to lose their carefully folded shapes, and the bonds that hold them together start to break. It's a narrow range, a delicate balance, but it's one that your body maintains effortlessly day and night as you rest and as you move through the world. The stability we find in molecular bonds extends into the realm of crystal lattices, where atoms arrange themselves in patterns that repeat endlessly, like wallpaper extending in 3 dimensions. In a salt crystal, sodium and chloride ions alternate in a perfect cubic grid, each ion surrounded by 6 neighbors of opposite charge. This arrangement minimizes repulsion and maximizes attraction, creating a structure so stable that it can endure for centuries. The lattice is not rigid in the way we might imagine a steel beam, but rather it hums with tiny vibrations, each ion oscillating gently around its equilibrium position, held in place by the collective embrace of all its neighbors. When you dissolve salt in water, you're not destroying these bonds through violence. but rather offering the ion something even more appealing. Water molecules, with their bent shape and uneven charge distribution, surround each ion in a process called hydration. The partially negative oxygen atoms cluster around sodium ions, while the partially positive hydrogen atoms embrace chloride ions. The energy released by forming these new ion-water interactions compensates for the energy required to separate the ions from the lattice. It is a peaceful exchange, a trade of one stable arrangement for another, and the ions drift apart into solution, each one cradled by a sphere of water molecules. Metallic bonding offers yet another vision of stability, one based not on the pairing of specific atoms, but on communal sharing. In a piece of copper or iron, the metal atoms release their outer electrons into a shared sea that flows throughout the entire structure. These delocalized electrons belong to no single atom, but to all of them collectively, moving freely like a fluid that holds the positive metal ions in place. This electron sea is what gives metals their characteristic properties, their ability to conduct electricity and heat, their malleability, their lustrous shine. The bonds are strong yet flexible, allowing metal atoms to slide past one another without breaking the overall structure, which is why you can bend a copper wire or hammer gold into thin sheets. The strength of metallic bonds varies with the number of electrons each atom contributes to the sea. Sodium, with just one valence electron, forms relatively weak metallic bonds, which is why sodium metal is soft enough to cut with a knife. Tungsten, contributing more electrons and having a more complex electron configuration, forms bonds so strong that it has the highest melting point of any metal, remaining solid until temperatures exceed 3,400 degrees Celsius. Yet, even tungsten's strength is not a matter of force, but of harmony, each atom held in place by the collective presence of the electron sea, a stability born from cooperation rather than constraint. Covalent network solids represent another extreme of stability, structures where every atom is connected to its neighbors by strong covalent bonds extending throughout the material. Diamond is the most famous example. Each carbon atom bonded to 4 others in a tetrahedral arrangement that repeats in all directions. There are no individual molecules in diamond, no small units that can be separated without breaking covalent bonds. The entire crystal is, in a sense, one enormous molecule, and this is why diamond is so extraordinarily hard. To scratch or break diamond, you must rupture countless covalent bonds simultaneously, and those bonds, as we have seen, are among the strongest in nature. Graphite, also made purely of carbon, demonstrates how structure determines stability in surprising ways. In graphite, carbon atoms form flat sheets of hexagonal rings, each atom bonded to 3 neighbors in the same plane. Within each sheet, the bonding is strong, but between the sheets, only weak van der Waals forces hold the layers together. This is why graphite feels slippery and why it works as a lubricant and as the lead in pencils. When you write, you are not breaking strong covalent bonds, but simply allowing the weakly held layers to slide over one another and transfer to the paper. The same element, carbon, creates 2 materials with vastly different properties, all because of how the atoms choose to arrange themselves and share electrons. Silicon dioxide, the primary component of sand and quartz, forms another covalent network, with each silicon atom bonded to 4 oxygen atoms and each oxygen bonded to 2 silicons. This creates a 3-dimensional framework of extraordinary stability, which is why quartz crystals can survive for billions of years, outlasting mountains and witnessing the slow drift of continents. The bonds are strong, the structure is rigid, and the material resists chemical attack from most substances. When you hold a grain of sand, you are holding a tiny fragment of this ancient, stable network, a structure that has found its energetic minimum and has no reason to change. Molecular crystals offer a gentler form of stability, where intact molecules are held together not by covalent or ionic bonds, but by intermolecular forces. Ice is a molecular crystal, each water molecule retaining its identity, while hydrogen bonding to four neighbors in a tetrahedral arrangement. This creates an open, spacious structure, which is why ice is less dense than liquid water and floats on its surface. The hydrogen bonds are individually weak compared to covalent bonds, which is why ice melts at a relatively low temperature, but collectively they create a stable, ordered solid that can endure the coldest winters. Dry ice, solid carbon dioxide, is another molecular crystal held together by even weaker London dispersion forces. Because these forces are so weak, dry sublimates directly from solid to gas at temperatures above -78 degrees Celsius, never passing through a liquid phase at normal atmospheric pressure. The molecules simply gain enough thermal energy to overcome the weak intermolecular attractions and drift away into the air. It is a reminder that stability is always relative, always dependent on conditions, and that even the most solid-seeming substance is just a temporary arrangement of atoms held together by forces that can be gently overcome. The concept of lattice energy quantifies the stability of ionic solids, measuring the energy required to completely separate 1 mole of an ionic compound into gaseous ions. Sodium chloride has a lattice energy of about 786 kilojoules per mole, a substantial amount reflecting the strong electrostatic attractions in the crystal. Magnesium oxide, with doubly charged ions, has a lattice energy exceeding 3,000 kilojoules per mole, making it far more stable and giving it a melting point of nearly 3,000 degrees Celsius. These numbers are not arbitrary, but arise directly from Coulomb's law, the simple principle that attraction increases with charge and decreases with distance. Born-Haber cycles allow chemists to calculate lattice energies indirectly by considering the various steps needed to form an ionic compound from its elements. You begin with solid metal and gaseous nonmetal, add energy to atomize and ionize them, then release energy as the ions come together to form the lattice. By carefully accounting for each energy change, you can determine the lattice energy even when it cannot be measured directly. It is a beautiful example of how thermodynamics allows us to understand stability through indirect reasoning, tracing pathways through hypothetical steps to arrive at real, measurable quantities. The stability of a crystal is also influenced by its defects, the imperfections that inevitably arise in any real material. Point defects, where an atom is missing or out of place, create local disruptions in the lattice but often have minimal impact on overall stability. Line defects, or dislocations, are more significant, allowing planes of atoms to slip past one another and giving metals their ductility. Without dislocations, metals would be brittle, shattering rather than bending. The defects, rather than weakening the material, actually make it more useful, more adaptable, more able to absorb stress without catastrophic failure. Alloys exploit this principle deliberately, mixing different elements to create materials with properties superior to pure metals. Steel, an alloy of iron and carbon, is stronger than pure iron because the carbon atoms occupy spaces in the iron lattice and prevent dislocations from moving easily. Bronze, copper mixed with tin, was so important to human civilization that an entire age was named after it. Brass, stainless steel, titanium alloys. Each is a carefully designed combination of elements, each achieving a particular balance of strength, flexibility, corrosion resistance, and weight. The stability of these alloys is not accidental but engineered, a testament to our growing understanding of how atoms interact and arrange themselves. Phase diagrams map the stability of different states of matter as functions of temperature and pressure, showing where solids, liquids, and gases are most stable. Water's phase diagram reveals that ice can exist in more than a dozen different crystalline forms, each stable under specific conditions of temperature and pressure. At very high pressures, water forms exotic ices with structures quite unlike the familiar hexagonal ice that forms in your freezer. These high-pressure ices are thought to exist in the interiors of icy moons like Europa and Enceladus, stable under the immense weight of overlying ice and water. The triple point on a phase diagram marks the unique combination of temperature and pressure where solid, liquid, and gas coexist in equilibrium. For water, this occurs at exactly 0.01 degrees Celsius and a pressure of about 611 pascals, roughly 0.6% of normal atmospheric pressure. At this precise point, ice, liquid water, and water vapor are all equally stable, and tiny changes in conditions can shift the balance from one phase to another. It is a delicate equilibrium, a reminder that stability is often a matter of fine margins, of being poised between different possibilities. Supercritical fluids exist beyond the critical point, where the distinction between liquid and gas disappears. Supercritical carbon dioxide, for example, has properties of both phases. It can dissolve substances like a liquid and diffuse through materials like a gas. This makes it useful for extracting caffeine from coffee beans and for cleaning delicate electronic components. The molecules are neither tightly packed nor widely separated, but occupy an intermediate state, a kind of stability that defies our everyday categories and reminds us that matter is more fluid and adaptable than our simple classification suggests. The stability of glasses represents a different kind of order, or rather, a lack of it. Glass is an amorphous solid, a liquid that has cooled so quickly that its molecules did not have time to arrange themselves into a crystal lattice. Instead, they froze in a disordered state, creating a material that is solid in its mechanical properties, but liquid in its structure. Glasses are not in true thermodynamic equilibrium. Given enough time, they would slowly crystallize, but this process is so slow that ancient Roman glass is still amorphous after 2,000 years. Glass is a frozen moment, a snapshot of disorder held stable by kinetic barriers that prevent the atoms from rearranging. Polymers achieve stability through long chains of repeating units, covalently bonded into molecules that can contain thousands or even millions of atoms. Polyethylene, the plastic used in grocery bags and bottles, consists of long chains of carbon atoms, each bonded to two others and to hydrogen atoms. The chains are held together by van der Waals forces, which are individually weak but collectively significant because of the large surface area of the long molecules. This gives polyethylene flexibility and toughness, allowing it to bend without breaking and to resist tearing. Cross-linking between polymer chains creates materials with different properties. Rubber, when vulcanized, forms covalent crosslinks between its polymer chains, transforming a sticky, weak material into something elastic and durable. The crosslinks prevent the chains from sliding past one another permanently. So when you stretch rubber, the chains extend and align, but when you release the stress, the crosslinks pull them back into their original tangled configuration. This entropic elasticity, driven by the tendency of systems to maximize disorder, is what makes rubber bounce back. Thermosetting plastics take cross-linking to an extreme, forming so many covalent bonds between chains that the entire material becomes a single, rigid network. Bakelite, the first synthetic plastic, is a thermoset, hard and heat-resistant, because its molecules are locked into a three-dimensional framework. Once formed, thermosets cannot be melted and reshaped, unlike thermoplastics, which soften when heated. This irreversibility reflects a deep stability, a structure that has found a low-energy configuration and cannot easily be persuaded to change. The glass transition temperature marks the point where an amorphous polymer changes from a hard, glassy state to a soft, rubbery state. Below this temperature, the polymer chains are frozen in place, unable to move relative to one another. giving the material rigidity. Above it, the chains gain enough thermal energy to slide and rotate, making the material flexible. This transition is not a true phase change, but a gradual shift in molecular mobility, and it determines whether a plastic will be rigid or flexible at room temperature. Polystyrene, with a glass transition above room temperature, is hard and brittle. Polyethylene, with a transition far below, is soft and flexible. Liquid crystals occupy a fascinating middle ground between the order of crystals and the disorder of liquids. In a liquid crystal, molecules have some degree of orientational order. They tend to point in the same direction, but lack the positional order of a true crystal. This partial order gives liquid crystals unique optical properties, which is why they are used in displays for watches, phones, and computers. The molecules can be reoriented by electric fields, changing how they interact with light, and they do so quickly and with low energy, a stability that is responsive rather than rigid. The stability of colloids and emulsions depends on preventing particles or droplets from aggregating. Milk is an emulsion of fat droplets in water, stabilized by proteins that coat the droplets and prevent them from merging. Mayonnaise is similar, with egg yolk proteins stabilizing oil droplets in vinegar. Without these stabilizers, the components would separate, oil rising to the top, but the proteins create a kinetic barrier that keeps the emulsion stable for weeks or months. It is a stability maintained not by thermodynamics, but by kinetics, by making the path to separation slow enough that it does not occur on practical timescales. Surfactants, molecules with both hydrophobic and hydrophilic parts, stabilize emulsions by positioning themselves at the interface between oil and water. The hydrophobic tail dissolves in the oil, the hydrophilic head in the water, and the surfactant reduces the interfacial tension, making it easier for small droplets to form and harder for them to coalesce. Soap works this way, surrounding grease and oil with micelles, tiny spheres with hydrophobic interiors and hydrophilic exteriors that can be rinsed away with water. The stability of these micelles is dynamic, constantly forming and breaking apart, yet persistent enough to clean effectively. Biological membranes are stabilized by lipid bilayers, two layers of phospholipid molecules arranged with their hydrophobic tails facing inward and their hydrophilic heads facing outward toward the aqueous environment. This arrangement is thermodynamically favorable because it minimizes unfavorable interactions between water and the hydrophobic tails. The bilayer is fluid, with lipids and proteins diffusing laterally within the plane of the membrane. Yet it is also stable, forming a barrier that separates the cell's interior from its surroundings and allows life to maintain the chemical gradients essential for metabolism. The stability of proteins depends on a delicate balance of forces. Hydrogen bonds, disulfide bridges, ionic interactions, and hydrophobic effects all contribute to folding a linear chain of amino acids into a specific three-dimensional shape. This shape determines the protein's function, and even small changes can render inactive. Proteins are only marginally stable, typically just a few tens of kilojoules per mole more stable in their folded state than unfolded. This marginal stability is actually advantageous, allowing proteins to be flexible, to change shape in response to signals, and to be degraded and recycled when no longer needed. Chaperone proteins assist other proteins in folding correctly, preventing them from aggregating or misfolding. They do not provide information about the correct fold that is encoded in the amino acid sequence, but they create a protected environment where folding can occur without interference. Misfolded proteins can aggregate into insoluble clumps, which is implicated in diseases like Alzheimer's and Parkinson's. The stability of properly folded proteins is thus not just a matter of thermodynamics, but also of kinetics and quality control, of ensuring that proteins reach their correct, functional state and avoid pathological alternatives. Enzyme stability is crucial for their function, and many enzymes are stabilized by cofactors, metal ions, or prosthetic groups that bind tightly and help maintain the correct shape. Some enzymes from extremophiles, organisms that live in boiling hot springs or freezing Antarctic waters, have evolved extra stabilizing interactions that allow them to function under conditions that would denature most proteins. These adaptations often involve additional salt bridges or hydrophobic interactions, small changes that have large effects on stability and demonstrate how evolution fine-tunes molecular structures for specific environments. Nucleic acids, DNA and RNA, achieve stability through base stacking and hydrogen bonding. The double helix of DNA is stabilized by hydrogen bonds between complementary bases, adenine with thymine, guanine with cytosine, but also by the stacking of the flat, aromatic bases on top of one another, which creates favorable van der Waals interactions and reduces their exposure to water. The sugar phosphate backbone is negatively charged, and the repulsion between these charges is mitigated by the presence of positively charged ions in solution, which cluster around the DNA and neutralize some of the charge. The stability of the double helix varies along its length. Regions rich in guanine and cytosine, which form 3 hydrogen bonds per pair, are more stable than regions rich in adenine and thymine, which form only 2. This variation in stability is functionally important. DNA replication and transcription often begin at rich regions because they are easier to unwind. The molecule stability is thus not uniform but modulated, with different regions having different energetic barriers to separation, allowing the cell to control where and when the DNA is accessed. RNA, typically single-stranded, folds into complex, 3-dimensional structures stabilized by intramolecular base pairing and base stacking. Transfer RNAs, ribosomal RNAs, and many regulatory RNAs all depend on specific folding patterns for their function. The stability of these structures is again marginal, allowing them to be dynamic, to change shape in response to binding partners or chemical modifications. RNA's versatility as both information carrier and functional molecule reflects this balance between stability and flexibility. The hydrophobic effect, often invoked to explain protein folding and membrane formation, is actually an entropic phenomenon. When hydrophobic molecules are surrounded by water, the water forms ordered cages around them, decreasing entropy. When hydrophobic molecules cluster together, they reduce the surface area exposed to water, allowing the water molecules to become more disordered and increasing the overall entropy of the system. This increase in entropy is thermodynamically favorable, driving the aggregation of hydrophobic substances even though there is no direct attractive force between them. It is a subtle form of stability, arising not from bonds but from the statistical preferences of water molecules. Osmotic pressure is another colligative property that depends on the number of dissolved particles rather than their identity. When a solution is separated from pure solvent by a semi-permeable membrane, water flows across the membrane to dilute the solution, creating pressure. This osmotic pressure can be substantial. A 1 molar solution exerts an osmotic pressure of about 24 atmospheres. Cells regulate osmotic pressure carefully, using pumps and channels to control the concentration of ions and other solutes, maintaining stability by balancing the inward and outward pressures across the membrane. Buffers resist changes in pH by absorbing or releasing protons. A buffer typically consists of a weak acid and its conjugate base, which together can neutralize added acids or bases. Blood, for example, is buffered primarily by carbonic acid and bicarbonate, maintaining a pH near 7.4 despite the constant production of acidic metabolic byproducts. This stability is essential for life. Even small deviations in blood pH can disrupt enzyme function and cellular processes. The buffer works by shifting equilibrium, a dynamic stability that responds to perturbations and restores balance. Le Chatelier's principle generalizes this idea. When a system at equilibrium is disturbed, It responds in a way that counteracts the disturbance. Add a reactant, and the equilibrium shifts to produce more product. Increase the temperature of an exothermic reaction, and the equilibrium shifts toward reactants. This principle reflects the fundamental tendency of systems to resist change, to find a new balance point that accommodates the disturbance while minimizing its impact. It is a kind of molecular inertia, a reluctance to be pushed far from equilibrium. Feedback mechanisms in biological systems use Le Chatelier's principle to maintain homeostasis. When blood glucose rises, insulin is released, promoting glucose uptake and storage. When it falls, glucagon is released, promoting glucose release. These feedback loops create stability, not through rigid control, but through responsive adjustments, constantly sensing conditions and making small corrections. The stability of living organisms is thus dynamic, maintained by networks of reactions and signals that respond to internal and external changes. Thermodynamic stability and kinetic stability are not always the same. Diamonds, as we have noted, are thermodynamically less stable than graphite at room temperature and pressure, yet diamonds do not spontaneously convert to graphite because the activation energy for rearranging the carbon atoms is enormous. The diamond is kinetically stable, trapped in a high-energy state by an insurmountable barrier. Many substances we encounter are kinetically rather than thermodynamically stable, persisting not because they are in the lowest energy state, but because the path to that state is too slow to observe. Catalysts increase reaction rates by lowering activation energy, but they do not change the thermodynamic stability of reactants or products. A catalyst provides an alternative pathway with a lower energy barrier, allowing the system to reach equilibrium more quickly, but the position of that equilibrium remains the same. Enzymes are biological catalysts, often increasing reaction rates by factors of millions or billions, yet they do not violate thermodynamic principles. They simply make the inevitable happen faster, guiding molecules over energy barriers that would otherwise be nearly impassable. The Arrhenius equation quantifies the temperature dependence of reaction rates, showing that rates increase exponentially with temperature. This is because higher temperatures mean more molecules have sufficient energy to overcome the activation barrier. Even a small increase in temperature can have a large effect on rate, which is why refrigeration preserves food. Lowering the temperature slows the chemical and enzymatic reactions that cause spoilage. The stability of food and of many other materials is thus a matter of kinetics, of keeping molecules too cold to react. Transition state theory provides a more detailed picture, imagining that reactants must pass through a high-energy transition state before becoming products. The transition state is not a stable intermediate but a fleeting configuration, a molecular arrangement at the top of the energy barrier. Catalysts stabilize the transition state, lowering its energy and making it easier to reach. The stability of the transition state, paradoxically, determines how quickly reactants can become products, how quickly the system can move toward equilibrium. Reaction coordinates diagram these energy changes, plotting potential energy against a generalized measure of progress from reactants to products. The diagram shows the initial state, the transition state, and the final state, along with any intermediates. Exothermic reactions show products lower in energy than reactants. Endothermic reactions show products higher. The diagram is a map of stability, showing where the system is stable, where it is unstable, and what barriers it must cross to move from one state to another. Potential energy surfaces extend this idea to multiple dimensions, showing how energy changes as several bond lengths or angles vary simultaneously. For a simple reaction involving 3 atoms, the surface is three-dimensional and can be visualized as a landscape with valleys, hills, and saddle points. Reactants sit in one valley, products in another, and the transition state is at a saddle point, the lowest point along the path that crosses the ridge between valleys. Finding the lowest energy path over this surface is a central problem in computational chemistry, a way of predicting how molecules will react and how stable different configurations will be. Molecular dynamics simulations follow the motion of atoms over time, solving Newton's equations of motion for every atom in the system. These simulations reveal how molecules vibrate, rotate, and collide, how they explore the potential energy surface, and how they occasionally cross energy barriers to react. Watching a molecular dynamics simulation is like watching a dance, atoms moving in response to forces, forming and breaking bonds, finding new configurations. The simulations show that stability is not static, but dynamic, a matter of constant motion around equilibrium positions. Free energy, not just potential energy, determines stability under realistic conditions. Free energy combines enthalpy, a measure of energy, with entropy, a measure of disorder, weighted by temperature. At low temperatures, enthalpy dominates, and systems favor low-energy states. At high temperatures, entropy dominates, and systems favor high-disorder states. The balance between these drives determines what structures are stable, what reactions occur, and how matter organizes itself. The Gibbs free energy change for a reaction tells us whether it will proceed spontaneously. A negative change means the reaction is thermodynamically favorable. A positive change means it is unfavorable. But even favorable reactions may be slow if the activation energy is high, and unfavorable reactions can be driven forward by coupling them to favorable ones, as cells do when they use ADP to power otherwise unfavorable processes. Stability, in this broader sense, is about the balance of energy and entropy, about what is possible and what is likely. Entropy is often misunderstood as mere disorder, but is more precisely a measure of the number of ways a system can be arranged. A gas has high entropy because its molecules can be distributed in an enormous number of ways. A crystal has low entropy because there are relatively few arrangements that maintain the ordered lattice. When ice melts, entropy increases not because the water molecules become chaotic, but because they have more freedom to move and arrange themselves. The drive toward higher entropy is a drive toward greater possibility, toward exploring more of the available states. The second law of thermodynamics states that the total entropy of an isolated system always increases. This is why heat flows from hot to cold, why gases expand to fill containers, why concentrated solutions diffuse into dilute ones. It is the fundamental arrow of time, the reason that some processes are irreversible. Yet local decreases in entropy are possible, as when water freezes or proteins fold, as long as the surroundings experience a greater increase. Life itself is a local decrease in entropy, maintained by consuming energy and exporting entropy to the environment. Statistical mechanics connects the microscopic behavior of molecules to macroscopic thermodynamic properties. Entropy, temperature, pressure, all emerge from averaging over the countless possible states of a system's particles. The stability of a macroscopic system reflects the overwhelming probability that it will be found in or near its most probable state, the state with the highest entropy consistent with its energy. Fluctuations away from this state are possible but rare and short-lived, which is why macroscopic properties appear stable even though the underlying molecules are in constant motion. Partition functions in statistical mechanics encode all possible states and their energies, allowing calculation of thermodynamic properties. The partition function is a sum over states, each weighted by a factor that decreases exponentially with energy. States with low energy contribute more to the sum, but high-entropy states, even if individually higher in energy, can also contribute significantly if there are many of them. The balance between energy and entropy between the drive to minimize energy and maximize entropy is captured mathematically in the partition function and determines the equilibrium properties of the system. Quantum mechanics adds another layer to our understanding of stability. Electrons in atoms and molecules occupy discrete energy levels, and the stability of a molecule depends on which levels are filled. Bonding orbitals, lower in energy than the atomic orbitals from which they form, stabilize molecules when filled with electrons. Anti-bonding orbitals, higher in energy, destabilize molecules when occupied. The balance between filled bonding and anti-bonding orbitals determines bond order and bond strength. A quantum mechanical version of the idea that stability comes from occupying low-energy states. The Pauli exclusion principle, which states that no two electrons can occupy the same quantum state, is fundamental to the structure of atoms and molecules. It is why electrons fill orbitals in pairs with opposite spins, why atoms have shells and subshells, why the periodic table has a structure. Without the exclusion principle, all electrons would collapse into the lowest energy orbital, and matter as we know it would not exist. The principle creates a kind of quantum pressure, forcing electrons into higher energy states and giving atoms their size and chemical properties. Hund's rule, another quantum principle, states that electrons prefer to occupy separate orbitals with parallel spins before pairing up. This minimizes electron-electron repulsion and, in some cases, maximizes exchange energy, a purely quantum effect with no classical analog. Hund's rule explains the magnetic properties of atoms and ions, why oxygen is paramagnetic, and why iron can be magnetized. These quantum effects, though subtle, have profound consequences for stability and reactivity. Molecular orbital theory extends quantum mechanics to molecules, combining atomic orbitals to form orbitals that span the entire molecule. In diatomic nitrogen, for example, the atomic orbitals of the two nitrogen atoms combine to form sigma and pi bonding and anti-bonding orbitals. Electrons fill these molecular orbitals according to the same rules as atomic orbitals, and the resulting electron configuration explains nitrogen's strong triple bond and its chemical inertness. The stability of nitrogen gas, which makes up most of the atmosphere, is a direct consequence of its molecular orbital structure. Delocalization of electrons, as in benzene or in metals, increases stability by allowing electrons to occupy lower energy, more spread out orbitals. In benzene, the 6 pi electrons are not confined to individual double bonds, but are shared equally among all 6 carbon atoms, forming a cloud above and below the ring. This delocalization lowers the energy compared to a hypothetical structure with alternating single and double bonds, a stabilization called resonance energy or aromaticity. Aromatic compounds are unusually stable and unreactive, a stability that can be understood only through quantum mechanics. The uncertainty principle, which states that position and momentum cannot both be precisely known, has implications for molecular stability. Electrons confined to small regions, such as bonds, must have high momentum and thus high kinetic energy. This zero-point energy is the minimum energy an electron can have and is a purely quantum effect. It contributes to bond lengths and bond strengths, making bonds slightly longer and weaker than classical predictions would suggest. Even at absolute zero, molecules vibrate because of zero-point energy, a reminder that quantum systems are never completely at rest. Tunneling, another quantum phenomenon, allows particles to pass through energy barriers that would be insurmountable classically. Protons, being light, can tunnel through barriers, which is important in certain chemical reactions and in proton transfer processes. Tunneling is rare and usually slow, but becomes significant when classical pathways are blocked. It is a subtle form of instability, a way for systems to escape from seemingly stable configurations by exploiting the probabilistic nature of quantum mechanics. Isotope effects provide evidence for quantum tunneling and zero-point energy. Reactions involving hydrogen proceed faster than those involving deuterium, its heavier isotope, because the lighter hydrogen has a higher zero-point energy and a greater probability of tunneling. This kinetic isotope effect is used to study reaction mechanisms, revealing which bonds are broken in the rate-determining step. The effect is a reminder that even something as fundamental as mass influences stability and reactivity in ways that are purely quantum. The concept of hybridization, mixing atomic orbitals to form new orbitals suited for bonding, helps explain molecular geometry and stability. In methane, carbons 1s and 3p orbitals hybridize to form 4 equivalent sp superscript 3 orbitals pointing toward the corners of a tetrahedron. This arrangement maximizes the distance between electron pairs, minimizing repulsion and creating a stable, symmetric structure. Hybridization is a mathematical convenience rather than a physical process, but it provides a useful way to think about how atoms bond and why molecules have the shapes they do. Coordination compounds, where a central metal ion is surrounded by molecules or ions called ligands, exhibit stability that depends on the electronic structure of the metal and the nature of the ligands. Transition metals, with their partially filled d orbitals, can form strong bonds with ligands, creating complexes with vivid colors and diverse reactivities. The stability of these complexes is quantified by formation constants, which can span many orders of magnitude. Some complexes are so stable that they persist even in harsh conditions, while others are labile, exchanging ligands rapidly. Crystal field theory explains the colors and magnetic properties of coordination compounds by considering how the electric field of the ligands splits the energies of the metal's d orbitals. In an octahedral complex, for example, the d orbitals split into 2 groups, with 3 orbitals lower in energy and 2 higher. Electrons fill the lower energy orbitals first, and the energy difference between the groups corresponds to the energy of visible light, which is why many transition metal complexes are colored. The splitting also affects stability, with high spin and low spin configurations having different magnetic properties and reactivities. Chelation, where a ligand forms multiple bonds to a single metal ion, greatly increases stability. Ethylenediamine, for example, binds to a metal through 2 nitrogen atoms, forming a 5-membered ring. Chelate complexes are more stable than comparable complexes with separate ligands because the entropy cost of bringing the ligand and metal together is paid only once. This chelate effect is used in medicine, where chelating agents bind toxic metals like lead or mercury and allow them to be excreted. Hemoglobin, the protein that carries oxygen in blood, is a coordination compound where iron sits at the center of a porphyrin ring, a large chelating ligand. The iron binds oxygen reversibly, picking it up in the lungs and releasing it in tissues. The stability of the iron-oxygen bond is finely tuned, strong enough to bind oxygen at high concentrations, but weak enough to release it where needed. This balance is achieved through the protein structure, which adjusts the electronic environment of the iron, a beautiful example of how biology exploits molecular stability for function. Chlorophyll, the molecule that captures light energy in photosynthesis, is similar in structure to heme, but has magnesium instead of iron at its center. The magnesium is held by a porphyrin ring, and the entire molecule is stabilized by resonance, with delocalized electrons that absorb light efficiently. The stability of chlorophyll allows it to withstand the intense light and reactive oxygen species generated during photosynthesis, and its breakdown in autumn, when the protein scaffolding is dismantled, reveals the yellow and orange pigments that were hidden by the green. The stability of complexes is also affected by the hard-soft acid-base principle, which states that hard acids prefer to bind hard bases and soft acids prefer soft bases. Hard species are small, highly charged, and not easily polarized. Soft species are larger, less charged, and more polarizable. Metal ions like magnesium and calcium are hard and bind well to oxygen-containing ligands like water and carboxylates. Heavy metals like mercury and lead are soft and bind well to sulfur-containing ligands like cysteine residues and proteins, which is part of why they are toxic. The delicate interplay between stability and reactivity reveals itself most beautifully in the world of transition states and activation barriers. When molecules transform from one form to another, they must pass through a fleeting moment of higher energy, a threshold that separates what was from what will be. This temporary arrangement, neither fully reactant nor product, exists for only the briefest instant, yet it governs the speed and possibility of every chemical change. The energy required to reach this peak is called activation energy, and it acts as a gentle gatekeeper, ensuring that stable molecules do not spontaneously rearrange without cause. This barrier is why the oxygen and nitrogen in the air around you do not suddenly combust, why the proteins in your cells remain folded and functional, why the world maintains its quiet, dependable order. Stability, in this sense, is not absolute resistance to change, but rather a measured reluctance, a preference for remaining as one, is unless sufficient energy arrives to justify transformation. Catalysts offer a soothing resolution to this tension between stability and change. These remarkable substances lower the activation energy required for a reaction without being consumed in the process. They provide an alternative pathway, a gentler route over the energy landscape, allowing molecules to transform more readily, while still respecting the fundamental stability of the system. Enzymes and living organisms are exquisite catalysts, each one shaped precisely to guide specific reactions with extraordinary efficiency. The active site of an enzyme cradles its substrate molecule, stabilizing the transition state and reducing the energy barrier by tens of thousands of times. This is not magic, but rather the careful application of molecular recognition, electrostatic guidance, and geometric precision. The substrate fits into the enzyme like a key into a lock, or more accurately, like a hand into a glove that adjusts its shape to provide perfect support. Once the reaction completes, the product releases, and the enzyme returns to its original form, ready to guide another molecule through the same transformation. This cyclical process allows life to proceed at a pace compatible with existence, neither too fast nor too slow, maintaining the delicate balance that defines biological stability. The concept of molecular orbital theory deepens our understanding of why certain bonds form and others do not. When two atomic orbitals combine, they create two molecular orbitals, one lower in energy, called a bonding orbital, and one higher in energy, called an anti-bonding orbital. Electrons preferentially fill the bonding orbital, which stabilizes the molecule, while anti-bonding orbitals remain empty or only partially filled in stable compounds. The difference in population between bonding and anti-bonding orbitals determines the bond order, a simple number that reflects the strength and stability of the connection. A bond order of 1 corresponds to a single bond, 2 to a double bond, and 3 to a triple bond. When the bond order is 0, no stable bond forms, and the atoms drift apart. This framework explains why helium atoms do not bond with one another. Each helium atom has 2 electrons, and when 2 helium atoms approach, all 4 electrons must be accommodated in molecular orbitals. 2 fill the bonding orbital, but 2 must occupy the anti-bonding orbital, canceling the stabilization and leaving no net attraction. The result is that helium remains forever solitary, a noble gas content in its isolation, stable precisely because it does not seek connection. Oxygen molecules present a fascinating puzzle that molecular orbital theory elegantly resolves. Each oxygen molecule contains a double bond, but experimental evidence shows that oxygen is paramagnetic, meaning it is attracted to magnetic fields. This property indicates the presence of unpaired electrons, which seems contradictory for a molecule with all its electrons seemingly paired in bonds. Molecular orbital theory reveals that in oxygen, the two highest energy electrons occupy separate orbitals with parallel spins, rather than pairing up in a single orbital. This configuration, predicted by theory and confirmed by experiment, explains both the stability of the double bond and the magnetic behavior. The molecule is stable because the bonding orbitals are more populated than the anti-bonding ones, yet retains a subtle reactivity due to those unpaired electrons. This delicate balance makes oxygen both stable enough to exist freely in the atmosphere and reactive enough to participate in the controlled combustion that powers cellular respiration. The stability of oxygen is not passive inertness, but an active equilibrium, a readiness held in check by energy barriers and molecular geometry. The phenomenon of aromaticity represents one of the most profound expressions of molecular stability. Benzene, a ring of 6 carbon atoms with alternating single and double bonds, exhibits unusual stability that cannot be explained by simple bonding models. The molecule is planar, with each carbon atom forming 3 sigma bonds and contributing 1 electron to a shared pi system that extends above and below the plane of the ring. These 6 pi electrons are not localized between specific pairs of atoms, but are delocalized around the entire ring, forming a continuous cloud of electron density. This delocalization lowers the energy of the molecule significantly, making benzene far more stable than would be expected for a structure with alternating double bonds. The extra stability, called resonance energy or aromatic stabilization energy, amounts to about 150 kilojoules per mole, a substantial energetic advantage. This is why benzene does not readily undergo addition reactions that would disrupt the aromatic system. Instead, it prefers substitution reactions that preserve the delocalized pi electron cloud. The stability of aromatic compounds has profound implications for chemistry and biology, as aromatic rings appear in countless natural and synthetic molecules, from the amino acids in proteins to the bases in DNA to the active ingredients in many medicines. Huckel's rule provides a simple criterion for predicting aromaticity in cyclic, planar molecules. A molecule is aromatic, and thus especially stable, if it contains 4 n plus 2 pi electrons, where n is any whole number including 0. This means that molecules with 2, 6, 10, or 14 pi electrons can be aromatic, while those with 4, 8, or 12 pi electrons are typically anti-aromatic and less stable than their non-cyclic counterparts. Benzene, with 6 pi electrons, fits the rule perfectly. Cyclobutadiene, with 4 pi electrons, is anti-aromatic and highly unstable, existing only under special conditions. Larger aromatic systems, such as naphthalene with 10 pi electrons, also enjoy enhanced stability. This rule, derived from quantum mechanical calculations, offers a remarkably reliable guide to molecular stability, and it has been verified in thousands of compounds. The mathematical elegance of Huckel's rule mirrors the physical elegance of aromatic molecules themselves, structures that achieve stability through symmetry, delocalization, and the subtle mathematics of quantum mechanics. Steric effects introduce another dimension to molecular stability, one based not on electronic considerations, but on the simple physical space that atoms occupy. When atoms or groups of atoms are forced too close together, their electron clouds repel, creating strain that destabilizes the molecule. This is called steric hindrance, and it can prevent certain conformations, reactions, or structures from forming. A classic example is found in substituted cyclohexanes, where large groups prefer to occupy equatorial positions rather than axial positions. In the axial position, a bulky group is forced close to other axial hydrogen atoms on the same side of the ring, creating unfavorable interactions. In the equatorial position, the group extends outward into open space, minimizing repulsion. The energy difference between these conformations can be several kilojoules per mole, enough to strongly favor one arrangement over the other. This preference is not a matter of bonding or charge, but simply a consequence of atoms needing space. Steric effects also influence reaction rates and pathways, as bulky groups can block access to reactive sites, protecting certain parts of a molecule from chemical attack. Nature uses steric hindrance strategically, designing enzymes and receptors with carefully shaped pockets that admit only specific molecules while excluding others. Conformational analysis explores how molecules can adopt different shapes by rotating around single bonds. Unlike double bonds, which lock atoms into fixed positions, single bonds allow free rotation, giving molecules flexibility. However, not all conformations are equally stable. In ethane, the simplest molecule with a carbon-carbon single bond, rotation around that bond creates different arrangements of the hydrogen atoms on each carbon. When the hydrogens on one carbon are directly aligned with those on the other, the molecule is in an eclipsed conformation with higher energy due to electron repulsion. When the hydrogens are offset, the molecule is in a staggered conformation with lower energy and greater stability. The energy difference is small, only about 12 kilojoules per mole, but it is enough that at room temperature, ethane molecules spend most of their time in staggered conformations. This principle extends to more complex molecules, where multiple rotatable bonds create a vast landscape of possible shapes. Proteins fold into specific three-dimensional structures by exploring this conformational space, settling into the arrangement that minimizes overall energy. The stability of a protein's folded state depends on the cumulative effect of countless small preferences, each single bond adopting the conformation that best accommodates its neighbors. Ring strain is a special type of molecular instability that arises when bond angles deviate from their ideal values. Cyclopropane, a three-member carbon ring, is highly strained because the carbon-carbon-carbon bond angles are forced to be 60 degrees, far from the ideal tetrahedral angle of 109.5 degrees. This angular strain, combined with torsional strain from eclipsed hydrogen atoms, makes cyclopropane much less stable than open-chain propane. The molecule is reactive, readily undergoing ring-opening reactions that relieve the strain. Cyclobutane, with four-membered rings, is also strained, though less so than cyclopropane. Cyclopentane has minimal strain, and cyclohexane, with six-membered rings, is essentially strain-free when it adopts a chair conformation. This is why six-membered rings are so common in nature, appearing in sugars, steroids, and countless other biological molecules. The stability of cyclohexane arises from its ability to achieve both ideal bond angles and staggered conformations simultaneously, a geometric harmony that minimizes energy. Larger rings can also be strain-free, but they are more flexible and less rigid, sometimes introducing other complications. The study of ring strain reveals how molecular stability depends not only on the types of bonds present, but also on the geometric constraints imposed by molecular architecture. The chelate effect demonstrates how the arrangement of bonds can dramatically enhance stability. A chelating ligand is a molecule that can bind to a metal ion through two or more attachment points, forming a ring structure that includes the metal. This multidentate binding creates complexes that are far more stable than those formed by equivalent monodentate ligands, which attach at only one point. The enhanced stability arises primarily from an increase in entropy. When a single chelating ligand replaces multiple monodentate ligands, the number of free particles in solution increases, leading to greater disorder and thus a more favorable entropy change. The enthalpy change may be similar in both cases, but the entropy advantage tips the balance decisively in favor of the chelate. This effect is exploited widely in chemistry and biology. EDTA, a common chelating agent, binds metal ions so strongly that it is used to treat heavy metal poisoning and to sequester metal ions in industrial processes. Hemoglobin and chlorophyll both employ chelation, with iron and magnesium ions held securely within the embrace of large organic ligands. The stability provided by chelation is not brute strength, but elegant design, a consequence of thermodynamic principles that favor order in some places to create greater freedom in others. Solvation, the interaction between a solute and its surrounding solvent, plays a crucial role in molecular stability. When an ionic compound dissolves in water, the ions are surrounded by water molecules that orient themselves to stabilize the charges. Positive ions attract the oxygen atoms of water, which carry a partial negative charge, while negative ions attract the hydrogen atoms, which carry a partial positive charge. This solvation shell lowers the energy of the dissolved ions, making the solution more stable than the separated solid and solvent. The energy released during solvation, called the heat of hydration, can be substantial, sometimes exceeding the lattice energy that holds the solid together. When this happens, the compound dissolves spontaneously, driven by the favorable interaction between ions and solvent. In nonpolar solvents, ionic compounds do not dissolve well because the solvation energy is insufficient to overcome the lattice energy. This principle, often summarized as like dissolves like, reflects the fundamental importance of intermolecular forces in determining stability. A molecule is not stable or unstable in isolation. Its stability depends on its environment, on the forces that surround and support it. Hydrophobic effects provide another example of how environment shapes stability. Nonpolar molecules, such as oils or the hydrocarbon chains of lipids, do not form favorable interactions with water. When placed in an aqueous environment, these molecules disrupt the hydrogen bonding network of water, forcing water molecules into more ordered arrangements around the nonpolar solute. This decrease in entropy is thermodynamically unfavorable. To minimize this cost, nonpolar molecules cluster together, reducing the surface area exposed to water and allowing more water molecules to participate in normal hydrogen bonding. This aggregation is called the hydrophobic effect, and it is a major driving force in the folding of proteins and the formation of cell membranes. The hydrophobic core of a protein, where nonpolar amino acids cluster together away from water, is stabilized not by strong attractive forces between the nonpolar groups, but by the entropic advantage of freeing water molecules from ordered arrangements. Similarly, lipid bilayers form spontaneously in water because the hydrophobic tails of the lipids hide from the aqueous environment, while the hydrophilic heads interact favorably with water. The stability of these structures is a collective phenomenon, an emergent property of many weak interactions working in concert, guided by the thermodynamic imperative to maximize entropy. Protonation states and pH profoundly affect the stability of molecules, especially biological ones. Many molecules contain groups that can gain or lose protons, depending on the acidity of their environment. A carboxylic acid, for example, can exist in a protonated form with a neutral charge or a deprotonated form with a negative charge. The relative stability of these forms depends on the pH of the solution. At low pH, where protons are abundant, the protonated form is favored. At high pH, where protons are scarce, the deprotonated form dominates. The pH at which the two forms are equally populated is called the pKa, a characteristic value for each ionizable group. Proteins contain many ionizable groups, and their overall charge and stability depend on pH. At a specific pH, called the isoelectric point, a protein has no net charge, and it is often least soluble and most prone to aggregation at this pH. Enzymes have optimal pH ranges where their structure is most stable and their activity is highest. Deviations from this pH can disrupt salt bridges, alter hydrogen bonding patterns, and even cause the protein to unfold. The stability of a molecule in solution is thus not a fixed property, but a variable one, sensitive to the chemical context in which it exists. Redox stability, the resistance of a molecule to oxidation or reduction, is another critical aspect of chemical behavior. Some molecules readily donate electrons, acting as reducing agents, while others readily accept electrons, acting as oxidizing agents. The tendency to undergo these transformations is quantified by reduction potentials, which can be measured and compared. A molecule with a low reduction potential is easily oxidized, while one with a high reduction potential is easily reduced. The difference in reduction potentials between two species determines the driving force for electron transfer. In biological systems, redox reactions are carefully controlled by enzymes and cofactors that manage the flow of electrons through metabolic pathways. The electron transport chain in mitochondria, for example, consists of a series of molecules with progressively higher reduction potentials, ensuring that electrons flow smoothly from food molecules to oxygen, releasing energy in manageable steps. Antioxidants are molecules that protect cells by being easily oxidized themselves, intercepting reactive oxygen species before they can damage more critical molecules. The stability of a molecule with respect to oxidation or reduction depends on its electronic structure, its environment, and the availability of suitable partners for electron transfer. Isotope effects reveal subtle aspects of bond stability that depend on nuclear mass. Bonds involving heavier isotopes, such as deuterium instead of hydrogen, are slightly stronger and less reactive. This difference arises from quantum mechanical zero-point energy, the minimum energy that a bond possesses even at absolute zero. Heavier atoms have lower zero-point energy, making their bonds slightly more stable. This effect, though small, can be measured and has practical applications. Deuterated solvents are used in nuclear magnetic resonance spectroscopy because they do not interfere with the signals from hydrogen atoms in the sample. Kinetic isotope effects, where reactions involving heavier isotopes proceed more slowly, are used to probe reaction mechanisms and identify which bonds are broken in the rate-determining step. In biological systems, the substitution of deuterium for hydrogen can slow enzymatic reactions, providing clues about how enzymes work. These isotope effects remind us that stability is not a purely electronic phenomenon. The nuclei, though often treated as mere points of positive charge, also play a role through their mass and their influence on vibrational energy. Molecular symmetry contributes to stability in ways both obvious and subtle. Highly symmetrical molecules often have lower energy because their electron density is evenly distributed, minimizing repulsion and maximizing bonding. Benzene's six-fold rotational symmetry is intimately connected to its aromatic stability. Methane's tetrahedral symmetry ensures that all four carbon-hydrogen bonds are equivalent, with no directional preference that might create strain. Symmetry also has spectroscopic consequences. Symmetrical molecules have fewer distinct vibrational modes and simpler spectra, reflecting their internal harmony. In crystals, symmetry determines packing efficiency and lattice energy, with highly symmetrical molecules often forming more stable solids. Even in complex biological molecules, local symmetry can enhance stability. Protein quaternary structures, where multiple subunits assemble into a larger complex, often exhibit symmetry that distributes interactions evenly and stabilizes the assembly. Symmetry is a kind of molecular elegance, a balance that reduces energy and enhances stability through the even distribution of forces and charges. Tautomerism introduces a dynamic aspect to molecular structure, where molecules can exist in two or more interconvertible forms that differ in the position of a hydrogen atom in a double bond. Ketoenol tautomerism is a common example. where a molecule can exist as a ketone with a carbonyl group or as an enol with a hydroxyl group adjacent to a double bond. In most cases, the keto form is more stable, but the enol form can be present in small amounts, and the two forms rapidly interconvert. This equilibrium is sensitive to solvent, temperature, and the presence of catalysts. In some molecules, the enol form is stabilized by intramolecular hydrogen bonding or resonance, making it more prevalent. Tautomerism is important in the chemistry of nucleic acids. The bases in DNA can exist in rare tautomeric forms that pair differently, potentially leading to mutations if they occur during replication. The stability of a tautomer depends on the same factors that govern all molecular stability: bonding, resonance, strain, and solvation. The existence of tautomer reminds us that molecular structure is not always static. Molecules can flicker between forms, exploring different arrangements in search of the lowest energy state. Hyperconjugation is a subtle stabilizing interaction that occurs when electrons in a sigma bond interact with an adjacent empty or partially filled orbital, or with a pi system. This interaction delocalizes electron density, lowering the energy of the molecule. In carbocations, positively charged carbon species, hyperconjugation from adjacent carbon-hydrogen bonds stabilizes the positive charge. The more alkyl groups attached to the carbocation, the more hyperconjugation is possible, and the more stable the carbocation becomes. This explains why tertiary carbocations, with 3 alkyl groups, are more stable than secondary or primary carbocations. Hyperconjugation also affects the stability of alkenes. More substituted alkenes, where the double bond is adjacent to more alkyl groups, are generally more stable than less substituted ones. This principle is reflected in Zaitsev's rule, which predicts that elimination reactions tend to form the more substituted, and thus more stable, alkene. Hyperconjugation is a quantum mechanical effect arising from the overlap of orbitals and the delocalization of electrons, and it demonstrates that stability can emerge from interactions that are not traditional bonds, but rather subtle resonances between different parts of a molecule. Anomeric effects in carbohydrates reveal how electronic interactions can override steric preferences. In cyclic sugars, a hydroxyl group or other substituent attached to the anomeric carbon, the carbon derived from the carbonyl group, can occupy either an axial or equatorial position. Normally, steric considerations favor the equatorial position, but in many sugars, the axial position is preferred. This preference arises from a stabilizing interaction between a lone pair of electrons on the ring oxygen and the anti-bonding orbital of the carbon-oxygen bond at the anomeric position. This interaction, called the anomeric effect, lowers the energy of the axial conformer, making it more stable despite the steric cost. The anomeric effect is a manifestation of hyperconjugation and orbital overlap, and it plays a crucial role in determining the three-dimensional structures of carbohydrates and glycosidic bonds. It is a beautiful example of how molecular stability is determined by a balance of competing factors, with electronic effects sometimes outweighing steric ones, and how nature uses subtle quantum mechanical interactions to fine-tune the properties of biological molecules. Frustrated Lewis pairs represent a fascinating frontier in the chemistry of stability and reactivity. A Lewis acid is a molecule that can accept an electron pair, and a Lewis base is a molecule that can donate an electron pair. Normally, when a Lewis acid and base encounter each other, they form a stable adduct, a new molecule where the base donates electrons to the acid. However, if the acid and base are sterically hindered, they may be unable to form this adduct, creating a frustrated Lewis pair. Despite being unable to bond with each other, the pair retains the reactivity of both the acid and the base, and it can cooperatively activate small molecules such as hydrogen, carbon dioxide, or even unreactive hydrocarbons. The acid and base work together, the base donating electrons to the substrate while the acid accepts electrons, facilitating reactions that neither could accomplish alone. This concept has opened new avenues in catalysis and small molecule activation, demonstrating that stability and reactivity are not opposites, but complementary aspects of molecular behavior. A frustrated Lewis pair is stable in the sense that it does not collapse into a single product, yet it is highly reactive towards suitable substrates, embodying a dynamic balance between potential and action. Photostability, the resistance of a molecule to degradation by light, is essential for many applications and natural processes. Ultraviolet and visible light carry enough energy to break chemical bonds or promote electrons to excited states, potentially triggering unwanted reactions. Molecules with extended conjugated systems, where multiple double bonds alternate, can absorb light and dissipate the energy safely through internal conversion, returning to the ground state without breaking apart. This is why many dyes and pigments are based on conjugated structures. They absorb light of specific wavelengths, giving them color, but they do not decompose immediately upon exposure. However, prolonged exposure can still cause photodegradation, as excited states can lead to reactive intermediates that undergo further chemistry. Nature has evolved protective mechanisms, such as carotenoids in plants, which absorb excess light energy and dissipate it as heat, protecting the photosynthetic machinery from damage. Sunscreens contain molecules that absorb ultraviolet light and convert it to harmless heat, preventing it from reaching the skin. Photostability is a kinetic form of stability, a resistance to change over time under specific conditions, and it depends on the ability of a molecule to handle energy input without undergoing irreversible transformation. Vibrational spectroscopy offers a window into molecular stability by revealing the frequencies at which bonds vibrate. Each bond in a molecule acts like a tiny spring, oscillating at a characteristic frequency that depends on the masses of the atoms and the strength of the bond. Stronger bonds vibrate at higher frequencies, weaker bonds at lower frequencies. By measuring these vibrational frequencies using infrared or Raman spectroscopy, chemists can identify the types of bonds present in a molecule and assess their strength. A shift in vibrational frequency can indicate a change in bond strength due to hydrogen bonding, coordination to a metal, or other interactions. Vibrational spectroscopy is non-destructive and highly informative, providing a direct probe of molecular structure and stability. It reveals that molecules are not static objects, but dynamic entities, constantly in motion, their atoms vibrating, rotating, and flexing. Yet within this motion is order, each vibration occurring at a precise frequency determined by the forces holding the atoms together. The stability of a molecule is reflected in the regularity and predictability of these vibrations, a molecular heartbeat that continues as long as the bonds remain intact. Nuclear magnetic resonance spectroscopy provides another profound tool for understanding molecular stability and structure. Certain atomic nuclei, such as hydrogen, 1 and carbon-13, possess a property called spin, which makes them behave like tiny magnets. When placed in a strong magnetic field, these nuclei can absorb radio frequency energy and flip their spin orientation. The exact frequency at which this occurs depends on the electronic environment around the nucleus, which is influenced by nearby atoms and bonds. By measuring these frequencies, chemists can determine the connectivity and arrangement of atoms in a molecule with extraordinary precision. NMR spectroscopy can also reveal dynamic processes, such as conformational changes, bond rotations, and chemical exchange, providing insight into the flexibility and stability of molecular structures. In proteins, NMR can detect which regions are rigid and which are flexible, helping to identify stable cores and dynamic loops. The technique is non-invasive and can be performed in solution, allowing molecules to be studied in conditions close to their natural environment. NMR spectroscopy reminds us that molecular stability is not a single property, but a multifaceted concept, encompassing both the static arrangement of atoms and the dynamic fluctuations that occur around that arrangement. Computational chemistry has revolutionized the study of molecular stability by allowing scientists to calculate the energies and properties of molecules using quantum mechanical principles. Modern software can solve the Schrödinger equation, or approximations to it, for molecules containing hundreds of atoms, predicting bond lengths, bond angles, vibrational frequencies, and reaction energies with impressive accuracy. These calculations provide insight into why certain structures are stable and others are not, revealing the electronic factors that govern molecular behavior. Computational methods can also explore potential energy surfaces, mapping out how the energy of a system changes as atoms move, identifying stable minima, transition states, and reaction pathways. This capability is invaluable for understanding complex reactions, designing new molecules, and predicting properties before synthesis. Computational chemistry complements experimental work, offering a theoretical foundation that explains observations and guides future experiments. It shows that molecular stability is not a mystery, but a consequence of fundamental physical laws, laws that can be understood, calculated, and applied to solve practical problems. The concept of molecular recognition, where molecules selectively bind to specific partners, is central to biology and depends entirely on principles of stability. An antibody recognizes and binds to a particular antigen because the shape, charge distribution, and hydrogen bonding pattern of the antibody's binding site are complementary to those of the antigen. The resulting complex is stabilized by a multitude of weak interactions, hydrogen bonds, van der Waals forces, electrostatic attractions, and hydrophobic effects. No single interaction is strong enough to ensure specificity, but together they create a binding affinity that can be both highly selective and remarkably strong. Enzymes recognize their substrates through similar principles, and receptors on cell surfaces recognize signaling molecules, triggering biological responses. Molecular recognition is the basis of drug action. A drug molecule binds to a protein target because its structure is complementary, stabilizing a particular conformation or blocking a binding site. The stability of these molecular complexes is exquisitely tuned, strong enough to form when needed, but weak enough to dissociate when the interaction is no longer required. This dynamic stability is essential for the regulation and responsiveness of biological systems. Allosteric regulation demonstrates how stability can be modulated by distant interactions. Allosteric proteins have multiple binding sites, and the binding of a molecule at one site can affect the structure and activity at another site, sometimes far away in the three-dimensional structure. This communication occurs through subtle conformational changes that propagate through the protein, altering the stability and shape of the active site. Hemoglobin is a classic example. The binding of oxygen to one subunit increases the affinity of the other subunits for oxygen, a phenomenon called cooperative binding. This cooperativity arises because oxygen binding stabilizes a particular conformation of the protein, and this stabilization is transmitted to the other subunits. Allosteric regulation allows for sensitive control of molecular function, enabling proteins to respond to changes in their environment and to integrate multiple signals. The stability of an allosteric protein is not fixed, but responsive, shifting between different states in response to the presence or absence of regulatory molecules. This flexibility, far from being a weakness, is a sophisticated form of stability that allows for adaptability and control. The Gibbs free energy equation, which combines enthalpy and entropy into a single measure of stability, is one of the most powerful tools in chemistry. The change in Gibbs free energy for a process, written as delta G, equals the change in enthalpy, delta H, minus the temperature multiplied by the change in entropy, delta S. When delta G is negative, the process is spontaneous and thermodynamically favorable. When delta G is positive, the process is non-spontaneous and requires energy input. When delta G is 0, the system is at equilibrium with no net tendency to change. This equation captures the balance between energy and disorder, showing that a process can be favorable even if it requires energy input, as long as it increases entropy sufficiently. Conversely, a process that releases energy may not be favorable if it decreases entropy too much. The temperature term in the equation means that the relative importance of enthalpy and entropy changes with temperature. At low temperatures, enthalpy dominates, and processes that release heat are favored. At high temperatures, entropy dominates, and processes that increase disorder are favored. The Gibbs free energy provides a unified framework for understanding molecular stability, encompassing both the drive to minimize energy and the drive to maximize disorder. Le Chatelier's principle offers a simple yet profound insight into the stability of systems at equilibrium. It states that if a system at equilibrium is disturbed by a change in concentration, temperature, or pressure, the system will adjust to counteract the disturbance and restore equilibrium. This principle applies to chemical reactions, phase transitions, and even biological processes. If a product is removed from a reaction mixture, the reaction will shift to produce more product, maintaining the equilibrium constant. If the temperature is increased, the reaction will shift in the direction that absorbs heat, counteracting the temperature change. This self-correcting behavior is a manifestation of the stability of equilibrium states. They resist perturbation and return to balance when disturbed. Le Chatelier's principle is a reminder that stability is not rigidity, but resilience, the ability to absorb change and adapt without losing fundamental character. It shows that molecular systems, like all natural systems, seek balance, and that this balance is maintained through dynamic adjustments rather than static resistance. The study of molecular stability reveals a universe of order within apparent complexity. Every bond, every interaction, every structural feature reflects the operation of fundamental forces and principles. Atoms seek low energy and high entropy, and in doing so, they create the rich tapestry of molecules that make up the world. Stability is not a single property, but a multifaceted concept, encompassing thermodynamic favorability, kinetic persistence, structural integrity, and dynamic responsiveness. It is the reason why matter has form, why reactions follow predictable pathways, why life can exist and evolve. Understanding molecular stability is understanding the rules by which the material world operates, rules that are both simple in their foundations and intricate in their manifestations. As we explore these principles, we find not chaos but harmony, not randomness but order, a quiet assurance that the universe, at its most fundamental level, is comprehensible, predictable, and profoundly stable. The concept of molecular stability extends into the realm of supramolecular chemistry, where molecules organize themselves into larger structures through non-covalent interactions. These assemblies exist in a delicate balance, held together by hydrogen bonds, van der Waals forces, and electrostatic attractions working in concert. The stability of such structures depends not on any single strong bond, but on the cumulative effect of many weak interactions, like a choir where no single voice dominates, but the harmony emerges from all voices together. This principle governs the formation of molecular capsules, cages, and frameworks that can encapsulate smaller molecules, providing stability through gentle enclosure rather than tight binding. Self-assembly is one of nature's most elegant expressions of molecular stability. When the right molecules are brought together under appropriate conditions, they spontaneously organize into ordered structures without external direction. This process is driven by the system's tendency to minimize free energy, finding the most stable arrangement through countless molecular encounters and adjustments. The beauty of self-assembly lies in its simplicity and inevitability. Given the right components and conditions, the stable structure emerges naturally, like water finding its level or a ball rolling to the bottom of a valley. The final structure represents a local or global energy minimum, a place of rest where the molecules have found their most comfortable arrangement. Host-guest chemistry explores how one molecule, the host, can provide a stable environment for another molecule, the guest. The host typically features a cavity or binding site that complements the guest's size and shape, creating a stable complex through multiple weak interactions. This stability is highly selective. Only guests that fit properly can form stable complexes, much like a key fitting a lock. The stability of host-guest complexes depends on complementarity in shape, charge distribution, and hydrophobic or hydrophilic character. When host and guest match well, the complex can be remarkably stable, yet the interactions remain reversible, allowing the guest to be released when conditions change. This reversible stability is crucial in biological systems and molecular sensing applications. Rotaxanes and catenanes represent mechanically interlocked molecules where stability arises from topology rather than chemical bonds. In a rotaxane, a ring-shaped molecule encircles a linear molecule capped with bulky groups that prevent the ring from slipping off. In a catenane, two or more rings are interlocked like links in a chain. These molecules cannot be separated without breaking covalent bonds, yet the components are not chemically bonded to each other. Their stability is mechanical, arising from their intertwined geometry. This creates a unique form of molecular stability, where the structure persists not because bonds hold it together, but because the components cannot physically disentangle. The synthesis of such molecules requires careful design and often involves self-assembly processes that guide the components into their interlocked configuration before the structure is permanently locked. Molecular knots take this concept even further, with single molecular chains tied into trefoil knots, figure-8 knots, and more complex topologies. These knotted molecules are stable because untying them would require breaking the chain itself. The stability of molecular knots is purely topological. No matter how the molecule flexes or rotates, the knot persists. Creating these structures requires synthetic strategies that guide the molecule through the necessary crossings and loops before closing the chain. The resulting molecules are stable not because they occupy a particularly low-energy conformation, but because all other conformations require passing through impossibly high-energy states where bonds would break. This represents a form of kinetic stability taken to an extreme, where the barrier to change is essentially infinite. The concept of cooperativity describes how the binding of one molecule can affect the stability of subsequent binding events. In positively cooperative systems, the first binding event makes subsequent bindings more favorable, increasing stability progressively. Hemoglobin exhibits this behavior. When one oxygen molecule binds, it induces a conformational change that makes the next oxygen binding easier and more stable. This creates a sigmoidal binding curve rather than a simple hyperbolic one. Cooperativity allows molecules to respond more sensitively to changes in concentration, switching more sharply between bound and unbound states. The stability of each binding event is not fixed, but depends on the state of the entire molecule, creating an interconnected system where local and global stability influence each other. Negative cooperativity, conversely, occurs when the first binding event makes subsequent bindings less favorable. This can serve to broaden the response range of a molecular system, allowing it to respond across a wider range of concentrations. The stability of binding sites decreases as more sites become occupied, preventing saturation and maintaining sensitivity. This demonstrates that stability is not always maximized in biological systems. Sometimes moderate, tunable stability serves function better than the strongest possible binding. Evolution has crafted molecular systems with precisely calibrated stability, neither too strong nor too weak, but exactly suited to their biological role. Molecular machines are assemblies that can perform mechanical work through controlled changes in molecular structure and stability. These machines operate through cycles where molecular conformations shift in response to chemical, light, or electrical stimuli. Each state in the cycle represents a locally stable configuration, and the machine moves between these states through controlled destabilization and restabilization. Rotary motors, for instance, use light to drive a molecule through a series of stable conformational states, creating continuous rotation at the molecular level. The stability of each intermediate state must be carefully balanced, stable enough to persist, but not so stable that the machine gets stuck. These machines demonstrate that controlled instability, the ability to move between stable states, can be as important as stability itself. Molecular switches toggle between two or more stable states in response to external stimuli. A photochromic molecule, for example, might have two stable isomeric forms with different colors, switching between them when exposed to different wavelengths of light. Each form is stable in the dark, representing local energy minima separated by an activation barrier. Light provides the energy to cross this barrier, allowing the molecule to switch states. The stability of both states ensures that the switch retains its state until deliberately changed, creating molecular memory. This bistability is essential for information storage and processing at the molecular level, where each stable state can represent a bit of information. The concept of frustrated systems describes situations where molecules cannot simultaneously satisfy all their stability preferences. In spin-frustrated magnetic systems, geometric constraints prevent all magnetic interactions from adopting their lowest energy alignment. Similarly, in some molecular systems, steric constraints or geometric requirements prevent the molecule from achieving its globally most stable configuration. The result is a system that settles into a higher energy state because the path to the global minimum is blocked. These frustrated systems can exhibit unusual properties, including high reactivity or the ability to access multiple nearly equal energy states. Frustration demonstrates that stability is not always achieved. Sometimes molecules must settle for compromised configurations where competing factors cannot all be optimized simultaneously. Molecular origami describes the folding of single-chain molecules into complex three-dimensional structures. DNA origami, for instance, uses the predictable base pairing rules of DNA to fold a long strand into predetermined shapes. The stability of the final structure depends on the cumulative effect of hundreds or thousands of base pairs, each contributing a small stabilization. The folding process itself follows a pathway through various intermediate states, each more stable than the last, until the final configuration is reached. This demonstrates how simple local stability rules, in this case, complementary base pairing, can give rise to complex, globally stable structures. The predictability of these interactions allows researchers to design molecular structures with atomic precision, knowing that the molecules will spontaneously fold into the stable target configuration. The stability of molecular structures can be probed through unfolding experiments. By applying mechanical force to a protein or nucleic acid, researchers can measure the force required to unfold the structure, revealing the strength of the stabilizing interactions. These single-molecule experiments show that unfolding often occurs in discrete steps, with different structural elements resisting force to different degrees. Alpha helices, beta sheets, and loops each contribute differently to overall stability. The force required to unfold a structure provides a direct measure of its mechanical stability, complementing thermodynamic measures of stability. These experiments reveal that molecular stability is not a single number, but a complex property that depends on the direction and type of perturbation applied. Molecular stability plays a central role in the origin of life, where the first self-replicating molecules needed to be stable enough to persist, yet reactive enough to undergo replication. RNA is thought to have played a key role in early life because it combines both properties. It can fold into stable structures through base pairing, yet can also catalyze chemical reactions and carry genetic information. The stability of RNA structures depends on environmental conditions, including temperature, pH, and the presence of metal ions. In the prebiotic environment, cycles of wetting and drying, heating and cooling may have driven cycles of RNA folding and unfolding, facilitating replication and evolution. The balance between stability and reactivity in these early molecules set the stage for the emergence of biological complexity. The concept of kinetic proofreading describes how biological systems achieve high fidelity by exploiting differences in the stability of correct versus incorrect molecular interactions. In DNA replication, the polymerase enzyme not only selects nucleotides based on their initial binding stability, but also checks the stability of the resulting base pair after incorporation. Incorrectly paired nucleotides are less stable and are more likely to be removed before the polymerase continues. This two-stage selection process, each based on stability differences, reduces error rates far below what could be achieved by a single selection step. The system trades speed and energy efficiency for accuracy, using the subtle stability differences between correct and incorrect pairs to achieve remarkable fidelity. Molecular chaperones are proteins that assist other proteins in achieving their stable, native conformations. When proteins first emerge from the ribosome, they may fold incorrectly or aggregate with other proteins before reaching their stable structure. Chaperones provide a protected environment where proteins can fold without interference, and some chaperones actively unfold misfolded proteins to give them another chance to reach the correct structure. The chaperones themselves are stable proteins that undergo cycles of binding and release, using energy from ADP hydrolysis to drive the folding process. This demonstrates that achieving molecular stability in complex systems often requires assistance. The stable structure may be the thermodynamically favored one, but reaching it may require help navigating the complex energy landscape. Intrinsically disordered proteins challenge the traditional view that protein stability requires a well-defined three-dimensional structure. These proteins lack a stable fold under physiological conditions, existing instead as dynamic ensembles of many conformations. Yet they perform important biological functions, often binding to multiple different partners or serving as flexible linkers between structure domains. Their lack of a single stable structure is not a defect, but a feature that enables their function. These proteins demonstrate that stability and function are not always synonymous. Sometimes flexibility and disorder serve biological needs better than rigid stability. The stability of these proteins lies not in their structure, but in their sequence, which persists even as the conformation fluctuates. The concept of conformational selection describes how proteins can bind to ligands by shifting their conformational equilibrium. A protein may exist in multiple conformations, with a ligand-binding conformation being relatively rare in the absence of ligand. When the ligand is present, it binds selectively to this conformation, stabilizing it and shifting the equilibrium toward the bound state. The stability of the protein-ligand complex drives the conformational change, rather than the ligand inducing a change in a static structure. This model emphasizes that proteins are dynamic entities constantly sampling different conformations, with stability determining the relative populations of each state. Ligand binding simply shifts the balance by stabilizing one particular conformation. Molecular stability is intimately connected to the concept of chemical potential, which describes the tendency of molecules to move from regions of high chemical potential to low chemical potential. In a solution, molecules diffuse from high concentration to low concentration because this reduces the system's chemical potential and increases stability. At equilibrium, the chemical potential is uniform throughout the system, representing a state of maximum stability with respect to molecular distribution. This principle governs not just simple diffusion, but also phase transitions, chemical reactions, and the distribution of molecules across membranes. Understanding chemical potential provides a unified framework for understanding many aspects of molecular stability and behavior. The stability of emulsions and colloidal suspensions depends on the balance between attractive and repulsive forces between dispersed particles. In an emulsion of oil droplets and water, the droplets tend to coalesce due to van der Waals attractions, which would destabilize the emulsion. Surfactant molecules stabilize emulsions by coating the droplets and providing repulsive forces, either electrostatic repulsion from charged head groups or steric repulsion from bulky molecular structures. The stable emulsion represents a kinetically trapped state where coalescence is prevented by an energy barrier, even though the separated phases would be thermodynamically more stable. This demonstrates again how kinetic stability can maintain structures that are not thermodynamically favored, allowing metastable systems to persist for practical timescales. Molecular imprinting creates synthetic materials with stable binding sites tailored to specific target molecules. The process involves polymerizing monomers around a template molecule, then removing the template to leave behind a cavity that complements the template's shape and functional groups. The resulting material has stable binding sites that can selectively recognize and bind the target molecule. The stability of these binding sites arises from the rigid polymer matrix that preserves the cavity's shape and the carefully positioned functional groups that interact with the target. Molecularly imprinted polymers demonstrate how stability can be engineered into materials, creating synthetic receptors with selectivity rivaling that of biological molecules. The phenomenon of molecular recognition underlies much of biological function and synthetic chemistry. Two molecules recognize each other when their shapes, charges, and functional groups complement each other, allowing them to form a stable complex. Recognition requires more than simple attraction. It requires specificity, the ability to distinguish the correct partner from similar alternatives. This specificity arises from the stability difference between correct and incorrect complexes. The correct complex is stabilized by multiple favorable interactions that fit together like puzzle pieces, while incorrect complexes lack some of these interactions and are less stable. The stability difference may be small in absolute terms, but it can be sufficient to drive highly selective recognition in complex mixtures. The concept of preorganization explains why some host molecules bind guests much more stably than others with similar functional groups. A preorganized host has its binding groups already arranged in the optimal geometry for guest binding, requiring little conformational change upon complexation. A non-preorganized host must pay an entropic cost to organize its binding groups around the guest, reducing the overall stability of the complex. Preorganization is a key principle in the design of synthetic receptors. By building the binding site geometry into the host structure, chemists can achieve much stronger and more selective binding. This demonstrates that the stability of a complex depends not just on the interactions in the bound state, but also on the cost of reaching that state from the unbound state. Molecular stability influences the rates of chemical reactions through the Hammond postulate, which relates the structure of transition states to the stability of reactants and products. For an exothermic reaction where products are much more stable than reactants, the transition state resembles the reactants in structure and energy. for an endothermic reaction where products are less stable. The transition state resembles the products. This principle helps chemists predict reaction mechanisms and design better catalysts by understanding how stability differences between reactants and products affect the reaction pathway. The transition state, being a high-energy, unstable configuration, is difficult to study directly, but its properties can be inferred from the stability of the species on either side of it. Molecular dynamics simulations allow researchers to watch molecules move and explore their stability landscapes in silico. By calculating the forces on each atom and integrating Newton's equations of motion, these simulations show how molecules vibrate, rotate, and transition between conformations. Over the course of a simulation, a molecule samples many configurations, spending more time in stable, low-energy regions and less time in unstable, high-energy regions. The resulting trajectory reveals the molecule's conformational preferences and the barriers between different states. These simulations complement experimental studies by providing atomic-level detail about molecular motion and stability, though they require careful validation to ensure that the calculated forces and energies accurately represent reality. Free energy perturbation is a computational technique for calculating stability differences between similar molecules or states. By gradually transforming one molecule into another in a simulation and measuring the energy changes along the way, researchers can calculate the free energy difference between them. This technique is particularly useful for drug design, where it can predict how modifications to a drug molecule will affect its binding stability to a protein target. The calculations are demanding, requiring extensive sampling to obtain accurate results, but they provide quantitative predictions of stability differences that can guide experimental work. This demonstrates how computational chemistry has become an essential tool for understanding and predicting molecular stability. The stability of molecular systems is fundamentally connected to information and entropy through the concept of Maxwell's demon. This thought experiment imagines a tiny being that could sort fast and slow molecules, apparently decreasing entropy and increasing order without doing work. The resolution of this paradox reveals that acquiring the information needed to sort molecules requires energy and generates entropy, so the second law of thermodynamics is preserved. This connection between information, entropy, and stability has profound implications for understanding biological systems, which maintain their stable, ordered structures by constantly processing information and expending energy. Life itself can be viewed as a system that uses information to maintain molecular stability far from equilibrium. Molecular stability plays a crucial role in the storage and transmission of genetic information. DNA's stable double helix protects the genetic code from chemical damage, with the bases tucked inside the helix away from reactive species. The stability of base pairing ensures that the two strands remain associated, yet the hydrogen bonds are weak enough that the strands can be separated when needed for replication or transcription. Errors in DNA replication are rare because the stability of correct base pairs exceeds that of incorrect pairs, allowing the polymerase to discriminate. When damage does occur, repair enzymes recognize the resulting instability, mismatched bases, or damaged structures that disrupt the regular helix geometry, and correct it. The entire system of genetic information storage and transmission relies on the predictable stability of molecular interactions. Epigenetic modifications add another layer of stability control to genetic information. Methyl groups attached to DNA or chemical modifications to histone proteins can create stable patterns of gene expression that persist through cell divisions. These modifications don't change the DNA sequence, but alter the stability of DNA-protein interactions, making some genes more or less accessible. The stability of epigenetic marks varies. Some are maintained stably through many cell divisions, while others are more dynamic, responding to environmental signals. This creates a flexible system where genetic information is stable, but gene expression can be tuned, allowing cells with identical DNA to adopt different stable states with different functions. The concept of a fitness landscape in evolutionary biology is analogous to an energy landscape in chemistry. Each genotype occupies a position in this landscape, with height representing fitness rather than energy. Stable species occupy fitness peaks, where most mutations would decrease fitness. Evolution proceeds through populations exploring this landscape, moving uphill toward greater fitness. However, populations can become trapped on local fitness peaks, unable to reach higher peaks because the path between them passes through valleys of lower fitness. This is analogous to kinetic stability in chemistry, where molecules occupy local energy minima. The stability of a species or population depends not just on its current fitness, but on the landscape around it. A species on a broad, high plateau is more stable than one on a narrow peak. Molecular stability extends into the realm of material science, where the stability of crystal structures determines material properties. Polymorphism, the ability of a substance to crystallize in multiple structures, arises when different crystal packing arrangements have similar stability. Diamond and graphite are both crystalline forms of carbon, with diamond being thermodynamically more stable at high pressure and graphite at low pressure. Yet, both forms persist indefinitely at room temperature and pressure because the kinetic barrier to transformation is enormous. This demonstrates how kinetic stability can preserve structures far from their thermodynamically stable form. Many pharmaceuticals exhibit polymorphism, and controlling which form crystallizes is crucial because different polymorphs can have different dissolution rates and bioavailability. The stability of glasses and amorphous materials presents a fascinating puzzle. Unlike crystals, glasses lack long-range order, yet they are mechanically stable solids. A glass is a supercooled liquid that has become so viscous that it behaves as a solid on human timescales, though it is not in thermodynamic equilibrium. The molecules in a glass are trapped in a disordered arrangement, unable to rearrange into the more stable crystalline form because molecular motion is too slow. Over extremely long timescales, centuries or millennia, some glasses may gradually crystallize, moving toward their thermodynamically stable state. This demonstrates that stability is time-dependent. What appears stable on one timescale may be slowly changing on another. Molecular stability influences the design of drugs and pharmaceuticals in many ways. A drug must be stable enough to survive storage, formulation, and passage through the body, yet reactive enough to interact with its biological target. The stability of a drug in the acidic environment of the stomach differs from its stability in a neutral environment of the blood or the interior of cells. Prodrugs exploit this by being stable, inactive molecules that are converted to active drugs by enzymes or chemical reactions in the body. The stability of drug-target interactions determines how long the drug remains bound and how effectively it modulates the target's activity. Medicinal chemists carefully tune molecular stability at every stage, balancing conflicting requirements to create effective therapeutics. The concept of molecular stability even extends to the quantum realm, where molecules can exist in superpositions of different states. In quantum chemistry, a molecule's wave function describes a probability distribution over many possible configurations, not a single definite structure. The stable states we observe correspond to eigenstates of the molecular Hamiltonian, where the wave function has a definite energy. When a molecule absorbs a photon, it transitions from one eigenstate to another, from one stable quantum state to a different stable state. The stability of quantum states is described by their lifetime. Excited states are generally less stable than the ground state and decay back down by emitting photons or transferring energy to other molecules. This quantum perspective reveals that even our concept of stable molecular structure is an approximation, a classical picture that emerges from the underlying quantum reality. Quantum tunneling allows molecules to overcome stability barriers in ways that classical physics would forbid. A particle can tunnel through an energy barrier rather than having to go over it, making reactions possible at temperatures where classical physics would predict the molecules lack sufficient energy. This is particularly important for reactions involving hydrogen atoms, which are light enough that tunneling is significant. Enzyme-catalyzed reactions sometimes exploit tunneling to achieve reaction rates faster than classical transition state theory would predict. The stability of reactants is thus somewhat illusory. Even molecules in stable configurations can undergo reactions through quantum pathways that bypass classical barriers. This adds a subtle quantum uncertainty to molecular stability, a reminder that the molecular world operates according to rules that differ from our everyday experience. The John Teller effect describes how molecular stability can drive distortions from high-symmetry structures. When a molecule in a highly symmetric configuration has degenerate electronic states, multiple states with the same energy, the molecule is unstable with respect to distortions that break the symmetry and lift the degeneracy. The distorted structure, though less symmetric, is more stable because it lowers the electronic energy. This effect is observed in many transition metal complexes, where octahedral coordination spheres distort to tetragonal or other lower symmetry geometries. The John Teller effect demonstrates that symmetry and stability are not always aligned. Sometimes breaking symmetry increases stability, and molecules naturally adopt the most stable structure, even if it lacks aesthetic appeal. Vibronic coupling describes how electronic and vibrational motions in molecules are interconnected, affecting stability. Electronic states depend on nuclear positions, and nuclear motion depends on electronic state. This coupling can stabilize certain conformations or lead to complex dynamics where electronic and nuclear motions are entangled. In photochemistry, vibronic coupling plays a crucial role in determining which products form after a molecule absorbs light. The excited electronic state may have a different stable geometry than the ground state, and as the molecule relaxes, the path it takes through the coupled electronic and nuclear landscape determines the outcome. Understanding vibronic coupling is essential for designing molecules with specific photochemical properties, such as photostable dyes or efficient light harvesting compounds. The concept of anti-aromaticity describes cyclic conjugated molecules that are destabilized by their electronic structure, while aromatic molecules are stabilized by delocalized electrons. Antiaromatic molecules with 4n-pi electrons are destabilized, making them less stable than analogous non-cyclic molecules. This destabilization arises from the electronic structure predicted by Huckel theory, where antiaromatic molecules have partially filled degenerate orbitals. Antiaromatic molecules are rare because they are so unstable. They tend to distort, rearrange, or react to escape the antiaromatic configuration. When chemists do synthesize antiaromatic molecules, they often exhibit unusual properties and high reactivity. Anti-aromaticity demonstrates that electronic structure can not only stabilize molecules, but also powerfully destabilize them, creating a driving force for structural change. Molecular stability in extreme environments reveals the limits and adaptability of chemical structures. Thermophilic organisms live at temperatures where most proteins would denature, yet their proteins remain stable through subtle modifications, additional salt bridges, more compact structures, or increased hydrophobic packing. Psychrophilic organisms thrive in freezing conditions with proteins that remain flexible and functional at low temperatures, achieving this through reduced stability that would be a liability in warmer environments. Halophilic organisms cope with high salt concentrations through proteins with highly acidic surfaces that remain hydrated even in concentrated salt solutions. These adaptations demonstrate that there is no universal optimal stability. The right stability depends on the environment, and evolution has found stable solutions across an enormous range of conditions. The stability of molecules in space presents unique challenges and opportunities for understanding chemistry. In the cold, low-density environment of interstellar clouds, molecules can persist in forms that would be unstable on Earth. Radicals and ions that would react instantly in terrestrial conditions can exist for long periods in space. Conversely, cosmic rays and ultraviolet radiation create a harsh environment that destroys complex molecules. The molecules detected in space, including water, ammonia, methanol, and even amino acids and sugars, are those whose stability allows them to survive these conditions. Studying the chemistry of space provides insights into the fundamental stability of molecules and the chemical processes that occurred in the early solar system before life emerged. Molecular stability is central to the field of astrobiology, which seeks to understand the chemical requirements for life. Life as we know it requires stable molecules that can store information, catalyze reactions, and form boundaries between inside and outside. The stability of these molecules must be tuned to the environment. Too stable, and they cannot participate in the dynamic processes of life. Too unstable, and they fall apart. The search for life elsewhere in the universe involves looking for environments where the right balance of stability and reactivity can exist. Liquid water is considered essential because it provides a medium where molecules can move and interact while maintaining sufficient stability. The temperature range where water is liquid, not too hot, not too cold, defines a habitable zone where the molecular stability requirements for life can be met. As we move through this landscape of molecular stability, we find that it is not a single simple concept, but a rich tapestry woven from thermodynamics, kinetics, quantum mechanics, and structural chemistry. Stability emerges from the interplay of forces at multiple scales, from the quantum behavior of electrons to the macroscopic properties of materials. It is both absolute and relative, both static and dynamic, both a destination and a journey. Every molecule, every bond, every interaction exists in a balance between order and chaos, between persistence and change. And in that balance, we find not just the foundations of chemistry, but the foundations of life itself, the stable yet dynamic molecular systems that make the living world possible. The journey through molecular stability reveals patterns that repeat at every scale. Atoms seek stable electron configurations. Molecules seek stable geometries. Proteins seek stable folds. And organisms seek stable internal environments. At each level, stability arises from the same fundamental principles: minimizing energy, maximizing entropy, balancing competing forces. Yet at each level, new properties emerge that cannot be reduced to the level below. The stability of a protein is more than the sum of its bond energies. The stability of a cell is more than the sum of its molecular components. This emergence of new properties at higher levels of organization is itself a form of stability, a robustness that allows complex systems to persist despite the constant flux of their components. In contemplating molecular stability, we find a source of deep calm. The universe, for all its complexity and change, operates according to consistent principles. Molecules naturally seek stable configurations, and the structures we observe, from the double helix of DNA to the crystals of snowflakes, emerge inevitably from these principles. There is no struggle, no effort, just a gentle unfolding of natural law. Every molecule, every bond, every interaction is exactly as it should be, occupying its place in the vast energy landscape of possibility. This naturalness, this inevitability, is profoundly reassuring. The molecular world is not chaotic but ordered, not random but lawful. not fragile but remarkably stable. And yet within this stability, there is room for change, for growth, for evolution. Stability does not mean stasis. The stable structures we observe are constantly in motion, vibrating, rotating, fluctuating. They exchange energy with their surroundings, respond to changing conditions, and occasionally transition to new stable states. This dynamic stability is what makes life possible. Molecules stable enough to persist, yet flexible enough to function. The same principles that create the stability of a diamond also create the dynamic stability of a living cell, where thousands of reactions proceed simultaneously, each molecule playing its role in the intricate dance of life. As we near the end of our exploration, we can rest in the knowledge that molecular stability is everywhere around us and within us. The proteins in our bodies maintain their stable folds, enabling the chemistry of life. The DNA in our cells preserves its stable structure, protecting the information that makes us who we are. The water molecules that make up most of our mass form their stable hydrogen bonds, creating the medium in which all our biochemistry occurs. We are, in a very real sense, made of stable molecular structures, and their stability is our stability. When we rest, we join the molecules in their low-energy states, finding our own equilibrium, our own place of calm. The study of molecular stability teaches us that strength comes not from rigidity, but from balance, not from resistance to change, but from the ability to find stability in new circumstances. The most stable molecules are often those that can adapt, that can flex without breaking, that can respond to their environment while maintaining their essential character. This is a lesson that extends beyond chemistry to life itself. We, too, find our greatest stability not in resisting change, but in adapting to it, not in holding rigidly to a single state, but in finding our balance as circumstances shift. In the quiet spaces between atoms, in the gentle vibrations of chemical bonds, in the slow conformational changes of proteins, we find a rhythm that mirrors the rhythm of rest. The molecular world does not rush. Reactions proceed at their own pace, determined by energy barriers and temperature. Molecules explore their conformational space gradually, sampling different configurations without haste. There is a patience in the molecular world, a willingness to wait for the right conditions, the right collision, the right alignment of energy and geometry. This molecular patience invites us to slow down, to let go of urgency, to trust that processes will unfold in their own time. The concept of equilibrium, central to molecular stability, offers a model for inner peace. At equilibrium, forward and reverse processes occur at equal rates, creating a dynamic balance where nothing changes at the macroscopic level, even though everything is in motion at the molecular level. This is not a static, frozen state, but a living balance, a stability that accommodates constant change. We, too, can seek this kind of equilibrium in our lives, not a rigid, unchanging state, but a dynamic balance where the various aspects of our lives move in harmony, where change and stability coexist peacefully. As we conclude our journey through the molecular world, we can appreciate the profound stability that underlies all of chemistry and all of life. From the simplest hydrogen molecule to the most complex protein, from the hardness of diamond to the flexibility of DNA, stability in its many forms shapes the material world. This stability is not imposed from outside, but emerges naturally from the properties of atoms and the laws of physics. It is a gift of the universe, a foundation upon which complexity can build, a ground of being that supports everything that exists. And so, as we return from our exploration of the molecular realm, we bring with us a sense of the deep order that underlies reality. We have seen how atoms bond together in predictable ways, how molecules find their stable configurations, how energy landscapes guide molecular behavior. We have learned that stability is not absolute but contextual, not simple but multifaceted, not static but dynamic. And we have found, in the calm predictability of molecular behavior, a reflection of the peace we seek in our own lives. You may rest now, knowing that the molecular world continues its gentle dance, bonds forming and breaking, molecules vibrating and rotating, all according to the timeless principles of stability. The atoms that make up your body are engaged in this same dance, maintaining the stable structures that sustain your life even as you sleep. You are part of the molecular world, subject to the same laws, finding your own stability in a vast energy landscape of existence. There is nothing you need to do, nowhere you need to go. You can simply be like a molecule in its ground state, at rest in the lowest energy configuration, stable and at peace. If you remain awake, more stories await, more gentle explorations of the scientific world, more opportunities to learn while you rest. But if sleep comes, welcome it. Let your mind settle like a molecule finding its stable conformation. Let your thoughts slow like a reaction, cooling toward equilibrium. Let yourself drift into the deep stability of rest. The molecular world will continue without your attention, stable and reliable, following its eternal patterns. And when you wake, it will still be there, unchanged in its essential nature, ready to reveal more of its quiet wonders. Thank you for joining this exploration of molecular bonds and stability. May you find your own stable state, your own place of rest and peace. May the gentle rhythms of the molecular world lull you into deep and restorative sleep, and may you wake refreshed with a new appreciation for the stable molecular structures that make life possible. Rest well, knowing that at the smallest scales, in the bonds between atoms, there is order, there is stability, there is peace. Good night.